Stream begins now. Wait. Bam. There we go. We're live. How about that? I'm a little bit groggy today. Been sleeping not that great, but it's fine. The show must go on. So, since last time, I've been doing some small thingies here and there, some cleanup, boring stuff. Good morning to you, Trill Crew. How are you doing? It's not morning, it's like 1 o'clock. I guess it's morning for some people. I've been doing some cleanup, boring stuff that I don't think is very good for the stream. But we have Duderinos moving around, spawning. You can shoot them. They shoot at you. They retaliate. You can make them infight with each other if you make them shoot each other as well. So that's pretty fun. So they will just eventually kill each other. There we go. Just great stuff. I'm happy to hear you're doing great, Trill Crew. So, what I want to do today is I want to do some collision stuff. So, you might see we might have some collision. We have some like projectile 2-unit collision stuff. And while that is for sure true, that's one type of collision that we have. I mean, it's the only we have right now. If we go take a look at it. So, here it is. All we're really doing is just doing a for each of all the units and checking if our, like the ray of the projectile, this frame, is colliding with that unit. So we're sort of looping through them and doing a manual sphere ray intersection check. Which is all fine and dandy. It's fantastic, but we probably want to do some more stuff. We want to have maybe some props out in the level, maybe a cube. And say like, you know, if you shoot the cube, then it should hit the cube, and so on. I'm programming, right now I'm programming, and hello Alan, by the way. I'm programming my game / engine, I guess. I don't really call it an engine, but it's something I'm making from scratch, because I think it's fun. It's a C++ standard stuff. But yeah, that's it. So it's just everything I'm doing from scratch, and that's just it. It's a little project. Yeah, so we want to make sort of a library of some sorts, so we can do more general collision checking. And to help with that, I made a little bit of an editor mode, I suppose. So you can press tab, bam, and you can go into a more standard editor view where you have a free camera, you can move around. All the graphics looks kind of weird, like the health bars looks strange, because they're assuming an orthographic view, but that's fine. We don't really care about this looking great. What we just want to do here is to sort of get a separate view of everything, so we can look at the collisions a bit more clearly to see, okay, are the normals looking good, is the penetration depth looking great, and everything is generally looking like they should. And also the shadow mapping is also a bit whack here, since the shadow frustrum is based on the camera, like the in-game camera. So the engine, the editor camera will not, it won't work correctly in that case. But it's fine. We can go back to this and keep playing, and we can go back, see like, oh, I'm being shot at by, oh, these guys are actually fighting each other here. And eventually they kill each other, bang. Oh, this guy's fine. Thank you. I don't agree, but thank you. It's a very nice compliment. There's definitely a lot to be done graphics-wise. Yes, so... Yeah, okay, and another thing I did to help out with this, to sort of set up for this this project, is that I made some code to just draw primitives, so drawing lines and drawing spheres and drawing points and so on, because I'm guessing that's gonna help us out. That's gonna help us out a lot when we're doing this collision code, so we can sort of visualize what's happening with the collision. So if I go into scene, for example, and I say I wanna unupdate, just draw a sphere, then I'll do something like scene, draw sphere. Oops. And it looks like this. So you have an origin, a radius, a color, and a duration. So this duration is kind of important. So it's gonna default to 0 if you look here in the header file. Here you can see it's like sort of defaulting to 0, right? So a 0 duration just means that it's gonna be drawn for 1 frame. So that means you have to call draw sphere every frame if you want it to be drawn like sort of permanently. Which is fine, which is usually how you want it. Like usually you want a sphere that sort of represents maybe the mouse or a collision or something, and the collision is gonna move every frame, so you want the sphere also to move every frame. So then you just have to keep calling it every frame, which is fine. Or if you want to say like, oh, I want to draw this line and I want it to be out for 5 seconds, then you just set duration to be 5, and it will be out for 5 seconds. So if I on scene update just draw a sphere somewhere, let's draw it at the origin, I suppose. So we'll just do vector 0 and a radius of, I don't know, 4, and then let's make it red. Apparently there's some threats. Did not find any threats since your last summary. Thank you for thank you for telling me that. So we'll make it red. Whoops. And then we'll run and we'll see we have a sphere here. It's sort of a, I guess, a metasphere or whatever you call it. It's not an actual sphere. I decided to go in this route instead because it's just easier to generate. I might make more lines later on just to make it sort of a bit more clear to see what is happening, but it's fine. So that's drawing every frame, and then we can also, of course, draw something for a duration. So let's say we want to draw a line in the beginning. So when we init the scene, we want to draw a line between 2 points. So let's draw it. That's from the origin to yeah, you just draw 5 units up. So it's gonna meet the sphere at the top, and then we'll make that blue, and we'll have it out for 5 seconds. So now there's a line there. Interestingly, it doesn't actually meet. Oh, whoa! That was too slow. I want to actually have a look. Oh, whoops! I want to actually have a look at it. So interestingly, did I make it actually 5 in radius? I made it 4 in radius. I'm dumb. So now if we look, there we go. We have a line going up to the sphere top, and then it disappears after 5 seconds. Quite neat, though. All right, so we have those. So that's gonna help us out a lot. So so yeah, so I've started a little bit with collision. So I've done these collision types, which are different types of collision types. Like there's rays, and there's planes, and there's lines, and there's spheres, and we're gonna have these sort of make functions for testing all of these with each other. Maybe not all of them, but I mean ray intersection and line intersection might not be super interesting, for example. But definitely stuff like, oh, you know, line sphere intersection is definitely gonna be one that we're gonna make. That's gonna be the projectile. Yeah, so I made that, and then I made the hit test function, the hit test file, which is for testing them all with each other. So we have the types, and then we have the actual hit testing, which we have here. And that returns this hit results struct, which if you ever worked in you know, Unreal or Unity probably looks pretty similar. Returns if it has a hit or not, and then it returns stuff like the position and the impact normal and the time. The time will only really make sense if it's array, or sorry, if it's a line or a trace rather, like either if it's a line trace or a sphere trace and stuff like that. Otherwise, it will just be 0. And later on, we're gonna have stuff like penetration depth and what do you call it? The minimum translation vector or whatever you call it. Yeah, so let's just start filling this out. So we have test array and plane. We have now, and we have test array and sphere. So these are the two that I'm actually using. So I was thinking we should fill those out first. So test array plane will just be if array is hitting a plane, or where array is hitting the plane. I made them, but I'm gonna remake them for this stream. So let's just remove them all. So let's start with test array plane. So that means, does array intersect the plane? And if so, where does it intersect? So if we draw this out, we will have something like, here's a plane, right? It has some normal, like so. And it has some position that's gonna be on this plane. So let's say it's just right here. It doesn't really matter where it is. And then we're gonna have array, which is gonna have some origin. So origin O, this is a vector. And it's gonna have some direction, which I'm gonna call D. I'll draw it with a hat, saying it's a normalized vector. And we call this vector here, like the point on the plane, we call that P. And then we have the normal of the plane, which is going to be n. Alright, so we have these 4 variables, which we can also see if we look in the code. Here's the structure for a plane, and of course we have the point and the normal. And for array, we have an origin and a direction. Fantastic. So how do we find the intersection of these? Let's see if I can actually remember this. This part I've done it a million times, but sometimes I forget the details. But let's just draw this a little bit more down, so it becomes a little bit easier direction. So what we want to find is this line here. Is if we sort of extend the array down to intersect the plane, we want to find this point here. This is what we want to find. Of course, though, we want to find, to get there, what we want to find is what this distance is. Like, how far does the ray have to travel to reach the plane? How far does the ray have to travel to reach the plane? And I'll call that t. Yeah, t for time. So this distance here, this distance from the origin of the ray to the plane here, we'll call that t. Alright, so we want to find t somehow. We don't know what it is right now. So we can construct a triangle quite easily, right? Because here's the hypotenuse, right? And then if I draw a line going from the ray down to the plane, so that it hits it at a 90-degree angle, we have this, what do you call it, isosceles triangle. I'm just gonna find out what the name is in English. Okay, it's just a right angle triangle. Okay, never mind. Okay, so a right angle triangle. Alright, so we have this right angle triangle. And we want to find what the hypotenuse is. So let's see here. So we can get this angle here. Oh, whoops. Or first, I guess we should get this one. So this is h. Let's call it h. This is the height of the oh, whoops. The height of the the ray origin from the plane. So getting that is quite trivial, I think. We sort of get the difference here. We get the difference from the plane point to the origin. So we'll do P. We'll get O minus P. So that's going to be our vector from our plane point to the origin of the ray. It's going to be this vector here. And again, it doesn't matter where the plane point is. It could be anywhere on this line. It doesn't really matter, as we'll see in a second. So it's going to be our O minus B. I should have drawn it a different color. It's fine. And now what we want to do is that we want to project this onto the plane normal. So we want to find, okay, how big is this vector in relation to the plane normal? So not considering it going from the side to the side, just how much is it going upwards? How much is it aligned with the plane normal? And again, just to sort of run you down how to project something onto a normal. If we have some normal vector here, start quite small actually, let's call it n. I'm doing a hat just to signify that this is a unit vector. And we have some other vector, doesn't matter where it is. Let's do this, v. And we want to find, okay, we want to project this down onto the normal line. If this is the normal line here, I'm just extending the normal vector. We want to project this down, like so, onto the normal span. So that it hits here at 90 degrees. So this resulting vector A here, I draw a vector here from this origin point here, up here. So this is A is going to be V projected down onto the normal line, right? And if we do another vector here, let's call this X. And I want to project this down, then of course we draw a line, the closest line to the normal span. Here, draw a vector, and it's going to be B. B is X projected onto the normal line. So you draw the closest line straight to the normal span, and that's where the projected vector is going to lie. All right. So to get so let's start with V to A. To get A, the first thing we have to find out is the length of A. Well, draw triangles won't help us find the projected vector, but it is a triangle. We could draw this triangle. So I hope you remember this. This is from the second course I did with you guys. I remember like more than 1.5 years ago. I did a math course with you guys. So this is what we went through then. So consider this a reminder. So first we can get the length of A, because the length of A is gonna be n dot v. And I won't go too much into the specifics, but n dot v is gonna be, it's gonna equal the length of A. So I do two lines to the next of it, on the sides, to say the length of. So it's two with a vector in the middle with two lines on each side means the length of vector A. So n dot v is gonna be the length of A. All right. So if we have the length of A, we also have the direction of A, because the direction of A is going to be the same as the normal. So these two will lie on the same line. A and n, by definition, since we're projecting onto n, will have the same directionality, will have the same span. So we can just do n times the length of A is gonna equal A. Alright? So if we have this, then we can just complete this and or sort of wrap this, I guess, into the same formula to say n times n dot v is equal to A. Alright? And this is the vector projection formula. All right. So this is how we project something onto any vector. So you can project one vector onto any other normal, I should say, not any other vector, since it has to be a unit vector. All right, so that's great. I'm just gonna move this to the side. So now that we can do that, we can figure out h, because h is gonna be this O minus P vector projected onto the N, the normal vector. And we don't even actually need the, we just want to find the height, like we just want to find the length of it. We don't care about the vector as a vector, like we don't really care about the direction, we just want to find the height of it, because we want this triangle. So we can sort of say, like, okay, this h is just gonna be O minus P dot product, excuse me, with the normal. And for a dot product, just to be clear, the order does not matter. We could write this, or we could write n dot O minus P. So as far as the dot product is concerned, it doesn't matter which order you do it in. Both are the same. We'll give you the same answer. So then we have h. So this is going to be equal to h. Like so. Alright. So, now that we have h, we want to find, if I just sort of erase this for now. There we go. Alright, so if we have h, then let's see if I remember my Sokatoa or so correctly. All I know is that we want to find this. We want to find this angle here, because if we have this angle and we have the one of the sides, then that is enough information for us to sort of complete the triangle. That's all we need, even because we have two pieces of information, and that will be enough for us to get the rest of it. So to get this angle, or rather to get the cosine of this angle, unless I'm thinking incorrectly. No, yes, I'm thinking, yes, okay, I'm thinking correctly. So to get this angle, we will do yes, exactly. So we will do the direction dotted with the normal. Alright? So we will do direction dot the normal. And actually, this I hope this makes sense, but we actually want to do dotted with the minus normal. Whoops. The minus normal. Because since the normal is pointing actually upwards, right? So if you look at this, the direction is pointing towards the plane, but the normal is pointing away from where we're going. Like it's pointing outwards while we're going inwards. So if we flip this, if we flip the normal, it will point downwards like this. The scale is not correct, that's fine. It's trust me that these have the same length. So then if we dot these, then if I draw it over here instead, normal. If we dot this, the normal here, and this is minus n. If we dot minus n with d, we'll get the cosine of the angle in between them, right? Because any vector A dot any vector B is going to be equal to the cosine of the angle in between them, I'm gonna draw that as a theta, the cosine of the angle between them times the length of A times the length of B. So this is another way to write the formula for dot product. Alright, so this is another way to think about dot product. So what we want is this cosine here, right? This cosine of the angle, because that will give us some more information about the triangle. The nice thing about them both being unit vectors, like with the little hats, right? Because they don't have a hat, so that means they have a length of 1, right? A unit vector has a length of 1, which means we can rewrite this formula as this. We can do a hat dot b hat is equal to the cosine of theta times, okay, so what's the length of A? It's a unit vector, which means it has a length of 1, so it's times 1. And then times what's the length of B? Well, it's also a unit vector, so it also has a length of 1 times 1. Well, timesing by 1 is not going to do anything. Any number times 1 is just itself, which means we can just disregard both of these two. Since they don't do anything, they change the formula anyway. So then we can rewrite this as a hat dot b hat is equal to the cosine of theta only, and nothing else. The cosine of theta, theta in this case is the angle in between the two vectors. Alright, so it's a nice fact about the dot product. Of course, this only works for two unit vectors. That's important to remember. If both of the vectors are not unit vectors, you will get a bigger number. You will not get only the cosine of theta. You will get it scaled by something. So it won't really make sense if you don't account for it. Yes. Okay. Cool. So we have the cosine of this angle here. If this is theta here. We have the cosine of the angle, and we have h here. Fantastic. So what do we do now? Well, let's see here. The problem here is I know the answer, but I've forgotten the logic about it. Okay, so I know it's gonna be h divided by the cosine of theta. All right, so that's what I know it is. So the cosine of theta is gonna be this length here. It's gonna be this edge, I think you just call it an edge, right, in a triangle. Yeah, it's gonna be this edge. Only that it's gonna be scaled down. So it's gonna be scaled down to if t was 1. So if t is 1, if t was 1, so if this triangle had a hypotenuse of 1, then it would be the length of this side. So then you divide them by each other. There is something here, but I don't remember. Is it SOHCAHTOA? I think it's SOHCAHTOA. Let's check it out. I should have looked this up before I did a stream, but it's fine. This is the way it goes sometimes. Right, so if we look, yeah, okay, so this is it. No, right, this is what I remember. So if you look at this, yeah, okay, so this will give us the answer. So here we have a formula. The cosine of theta is equal to the adjacent divided by hypotenuse. Alright? So let's take this formula out and write it down. So the cosine of theta, is equal to, what was it? Adjacent divided by, yeah, right. So I'm gonna write adj for adjacent divided by the hypotenuse. Right, so that's the formula. That's like SOHCAHTOA, you know. And I would advise you to think about why that's true. I think it's very interesting. It has to do with sort of It has to do with scaling up unit circles and the fact that the cosine of an angle is the x position of a point on a circle at angle theta. Very interesting. I might go over it someday. But yeah, so we have this formula, but of course we want the hypotenuse, right? So when I find back this formula, so if we have like a divided by b is equal to x, what we know is that if we times these two values, so if we times x by b, then it's going to equal to a, right? Because a divided by b is equal to x. So we scale something, we divide something by b, and then if we scale it up by b again, we'll get back to where we were, right? So that means x and b times together is equal to a. Well, any values x and b, the order doesn't matter, right? The order of b times x or x times b doesn't matter, which means we can sort of swap these two around and the formula should still hold. So if we swap them around, a divided by x is equal to b, then everything still holds together. B times x is equal to a, which is what we sort of established here. So we can do that sort of swap-a-rooney when we're doing having this type of formula. So that means we can swap these two around as well. So we have the cos of theta and the hypotenuse. So the cos of theta times the hypotenuse should equal the adjacent. So if we swap these two around, then we get the hypotenuse is equal to the adjacent. Whoops. The adjacent divided by the cosine of theta. And there we have it. So we have the hypotenuse, and that's t. So we know this is equal to t. Dang it. So, and that's what we were after. We were after t, because if we have t, then we can sort of just take the origin plus the direction times t, and that will travel along this line to the point where we hit the plane. Alright? So there we have it. So that's what we need to do. So first of all, we're gonna get this h. Whoops. We want to get this h here. So that's the first step. So into coding land we go. So test ray plane, ray and plane. Okay, cool. So yeah, okay. So we want to get h, and h was let's move. Okay, so it was n, the normal of the plane, dotted with O minus P, where O is the origin of the ray and P is the plane point. So we'll do plane to ray is equal to ray origin minus plane point, like so. So now we have the plane to ray vector. Fantastic. And then we'll get the height. So we'll call it ray height, honestly. Ray height is equal to plane to ray dotted with the plane normal. Right? So now we have the ray height, like this. Yep. Get the height of the ray from the plane. Next thing we want to do is find the angle, right? So again, the angle was the direction of the ray. Just losing my ability to talk. The direction of the ray dotted with the minus normal. Okay, so the minus normal. So this is important to remember. It's not the minus normal, because we wanted to point downwards. So we wanted to point in the direction the ray should be going to reach the plane. Get the angle of the ray compared to the normal. So So then we'll do ray angle is equal to dot ray direction with plane normal. And of course it's the minus plane normal. So now we have the angle. And now the final step is the time. So the time is, again, we do this swapperoo of SOHCAHTOA. The fact that we can swap this around with the adjacent divided by hypotenuse is equal to the cosine of theta, but well, if we have both of these two, and we want this, we want the hypotenuse, so we swap these two around and we get the hypotenuse. So, float, float impact time is equal to ray height divided by ray angle. Time to impact with plane. Alright. Yes. And we want to do... Yeah, so we want to just do a hit from this. We have this hit make. So it takes a position. So a position is going to be the impact point. And that's going to be ray origin plus ray direction times impact time. Right? So it starts from the origin and then we travel along the direction for this time here. Right? So the distance here is t. So it's from origin forwards for however long this is, for however long it has to travel to actually reach the plane. And that's going to be our impact points, like right there. The normal is just gonna be, for now, the plain normal. We'll see why that doesn't work later. And time, I guess we'll write the time. I don't know if it's ever gonna get used, but why not? We have time, so might as well use it. Okay, so ray origin plus ray direction times impact time. Fantastic. So let's try this out. So we'll go into editor. We'll do some tests, collision stuff. Alright, so we'll make a ray, and we'll set the ray to be from... Let's do from the camera. So that will be editor camera position. And we'll set its direction to be the editor camera. We'll get forward. It's a little bit. Let's see. We have the ed camera here, so we have a quaternion, which is its orientation. So we want to get the forward of that, and that's going to be x. So we'll do quat x plus. So I don't want to go straight forward because then we won't see it as clearly. So I wanted to go a little bit to the left as well, so we can actually see the ray. No, you know what, fuck it, we'll use position a little bit to the left, then it'll be easier to see. So I will do minus quat y. Times, simplify, doesn't really matter. So now we have a ray going from the camera's position and then just forward. Camera's position a little bit to the left. Actually a little bit to the right, now I think, because y is left, I believe. So we'll just draw this. So let's just draw. We'll just draw. Scene draw line from ray origin to ray origin plus ray direction times, I don't know, 20. I will make it red. No, we'll make it green. Yeah, let's make it green. So we'll do color green. Alright, so we don't have array. Okay, we don't have a lot of things actually, so let's import some stuff. First of all, we want collision types. That's in engine collision. So that's containing the ray stuff. And then we also want to include the scene, so we can draw lines. So we'll do runtime, game, scene. Is it test ray sphere must return a value? Oh, whoops. Okay, so this... There we go. Leave that for later. Alright, cool. So let's see what happens. So I'll go into editor mode, and there we have a line. Right, so it looks a little bit weird. It's a little bit hard to see sort of what's happening right now. Also, you can flip around with the camera. Should probably fix that at some point. So it's a little bit hard to see what's happening. So it did actually offset to the right, I believe. So the line is coming from the right here and then going forwards, right? It's going forwards, so it's sort of, you can imagine this as being a line that's pointing from your ear and in the direction that you're looking. So that's what happened. And you can see that here it's clipping with the ground here. So that's great. Okay, cool. So next thing we want to do is that we want to draw where it collides with the ground. So then we'll just use our cool function we just made. So tests ray plane. Oh yeah, we'll have to make the plane as well. So plane, and the plane is gonna be at just 0, the point, and at the origin, and then the normal is gonna be straight up. So it's gonna be just Z. So then we'll test them. So it's gonna be test ray and plane, and it's gonna return a hit results. So yes. So now we wanna draw where it hits and the normal of the hit. So we'll actually do scene draw point at the hit position. We'll make that red, and we'll draw a line from hit position to hit position plus hit normal. I'll make that red as well. Alright, I don't really see what could go wrong, and we gotta also include hit test. Alright, so we'll go into editor mode, and there we go. So now we can see that where the line is intersecting the ground, we get like a point, like there's where it's intersecting, and then we get the normal of the intersection as well. So that's nice. Great, but of course I know a bug is gonna happen when we go under the ground. So let's try that. I'll go under, and we're hitting the plane. However, the normal should be pointing downwards now, right? Because we're hitting the plane from the other side. So while the normal of the plane is pointing upwards, the hit here is actually downwards. So we're gonna have to fix that as well. And also, this is a little bit hard to see, so I'm actually gonna, you know what, I'm gonna just make the ray a global variable. And we will only update the ray's position if we're holding a key. So we're going to do input key down. That's a good key, R. We will only update the origin and direction when we're holding R. And what this will do for us there we go. So now if I hold here and I hit R, there we go. So now I'm updating the line, and if I let go of R and then move away, the line will stay there. So then we can sort of take a look at it from another angle and sort of verify that, yeah, this looks pretty good. But okay, I'm gonna show you a bug now. So if I look upwards like this, let go of R and then look behind, we can see that okay, it's actually detecting an intersection point here, even though it's behind the ray. So this could make sense, like you could make an argument for this being valid, saying that a ray is not only forwards, but a ray is also a backwards traveling thing. But in my case, I feel like in my engine I don't want this to be true. I want the ray to be a forward-facing thing, so it's gonna be a thing that travels forwards from an origin, it can't go backwards. Saying it goes backwards is invalid. So we want to do two things. We want to first make the normal be correct, and 2, we want to make sure that this doesn't happen. So we want to make sure that going backwards on a ray is not equal to a hit. Okay. So yeah. So let's do that. So how do we find out if the ray is under the plane? Well, if this... Let's see. So if this h is positive, so the h is the distance above the plane, right? If the h is positive, that means we're above the plane, right? Since this normal is pointing upwards, we're like sort of going to up the normal. But if this h is negative, that means we have a situation where our origin is actually behind, like this, right? So if this is our origin, and we dot that with the normal, we're gonna get a negative number here. So we're gonna get this negative triangle here, this negative h. So that means we're behind the normal, and since we're behind the normal, that means we are behind the plane, we're under the plane. So an easy way to fix this is just to do, okay, the normal is going to be the plane normal times the sine of ray height. So sine returns 1 if the ray height is positive, or like if the value is positive. But if the value is negative, then it's going to return -1. So it's just going to return if it's positive or negative, or 0 if the value is 0. But that's, I mean, hopefully it won't be a case. We might do I guess an edge case for that, but I don't think it's going to be necessary. So now, hopefully, we should return, okay, get the plane normal, but if ray height is negative, which means we're under the normal, then give us the minus normal. So then do plane normal times -1, which will just flip the normal. Oh, whoops. I started up the server when it's already started. Oh no, we don't have sine. Well, let's make it then. So, bunch of stuff here. I guess I'll put it here. Sine of float A. So that's gonna return if A is greater than 0, then return 1. And if otherwise, return -1. I actually, you know what, this is a little bit controversial, but I actually won't make it return 0 if the value is 0. I will just make it return 1. I think that makes sense. Because usually, especially since we're dealing with floating points, they're gonna be 0 so rarely that usually it's an error. If I'm calling sine with 0, it means I want to get something else out of it. It not technically makes sense, but you know what? I make the rules here. So okay, so we have editor mode, and I'm gonna hit E. No wait, sorry, R to bring it forward, and then I'm gonna go under the plane, and hopefully there we go. Nice. So the normal now is pointing downwards. It's pointing the way the ray is actually hitting the plane. And if I go up here, then it's gonna point upwards. Great, fantastic. So now that's bugs fixed. So now we should fix the bug where if I'm looking upwards, we're getting this invalid backwards hit, alright? So that is also quite easy to fix, because if we're going backwards, that means that this t value is negative. So if we have this scenario, let's see, maybe I should make this bigger. So if we have a scenario here, let's draw some lines. So here's a plane with some normal. And now we have the origin of the ray, and it's going off in this direction D. Then we have this scenario where, okay, so the triangle is gonna look like this. This was not a good case, but whatever. Let's just deal with it. So we have this t here that's going backwards. This t is gonna get negative, right? Because we're gonna get the thing that's gonna happen is that this cosine of this angle here is gonna get greater than 90 degrees. All right. So we're gonna have a triangle that looks kind of weird, and well, it's just a bad time. Or I mean, again, it sort of makes sense mathematically. A ray that can go backwards and forwards. It's nice that we can do that if we wanted to. But in our case, if we're seeing that impact time is negative, we have to go backwards in time to actually hit the plane. Then we just say, if impact time is less than 0, we say, okay, this was not a hit. We just return hit results. Use the plain non-hit. All right. So if we play and I fuck around with ray and move it upwards, then we don't see a hit. Of course, we see a hit here now though, because we're always drawing something. So a non-hit, like a non-initialized hit, will just have its position and normal be as 0. So that's why it's drawing a point at the origin, but no line, since the line is also 0, like the normal is just a 0 vector. So to save up from this, we might just do if hit has hit, then draw. So if it doesn't have a hit, then don't draw anything. Alright, so if we do tab, and then R, and then look upwards like this, so it's not hitting anything, then we don't see anything. Alright. So there's one last thing I want to save up on, that potentially could happen, is this scenario here. So that's, excuse me. So let's just sort of sudda this bot, and then I'll make a ray here, origin, and I'll make the direction be parallel with the plane, like this. So what will happen here, I mean, sort of conceptually, if you sort of think about it, is that the ray will never hit the plane. It will never hit the plane. It will just keep going forever, because the definition of two parallel lines, or not the definition, but one of the effects of two parallel lines is that they will never intersect. They will never intersect. And this is actually, like, at least in 2D, this is actually a sort of assumption you can make, that if two lines never intersect, then they are by definition parallel. And if they do have an intersection point, then they are by definition not parallel, unless they are the same line. Alright? And now that I think about it, we actually don't care, because this will never happen in code. Like when we're talking about actual codey stuff, this will never happen. Like, a floating point will always be so close to being 0. It will so rarely be exactly 0, unless you set it to be exactly that. And then I think it's fine if it sort of crashes. Or I guess no, wait, now that I said that out loud, maybe I'm not fine that it crashes. Okay, you know what, I changed my mind once more. So let's just do if is nearly 0, ray angle, then just return nothing. We say like, okay, it's parallel. Let's just do parallel check. They will never intersect. And the reason it will crash is that ray angle will be 0, right? Because the cosine of 90 degrees is 0. And then we get to this line here, where we do ray height divided by ray angle, and ray angle is going to be 0. You just might see where I'm going with this. It's going to be ray height divided by 0. So that will be a crash. Or no, it won't actually be a crash. It will be, this impact time will be indeterminate. Or not the number, I mean. So it will be a nan value. But then it will be like, sort of infect this hit, so this hit will become a nan hit. And it's just a big headache. So let's just sort of early out if that's nearly 0. It's quite cheap to do anyway, so it won't affect much. So, and here we'll do backwards check. We only care about forward hits, forward intersections. Like so. and let's double check again that it's actually working. So we'll do bang. Yeah, looks pretty good. And if I go downwards, then there we go. We get a down hit. Perfect. And if I go upwards and look up, then we get nothing. Nothing at the origin either. Sweet, perfect. So we have ray plane intersection done. I'm just gonna take a quick toilet break, and then I'll be back. So just give me 1 second. Can I? Yo, what up? Just 1 sec. All right, so let's see here. It's gonna shut down the skin. Whoa. Okay, so we have line plane intersection or ray plane intersection. Oh, whoops. Oh, that was weird actually. Wait, do I have this bug? No, doesn't seem like it. Oh, weird. All right. Anyways. So, and the next step would probably be maybe do rain sphere intersection. So let's say this would be a sphere that you could actually collide with, then we will expect to see like a normal on the surface of it, and so on. So let's do this. Let's first of all remove drawing the sphere from the scene. There. And then we'll go into, let's see, the editor, and we'll draw it in here instead. So, let's see. Ray plane intersection, and then we'll do ray sphere intersection. So we'll have a sphere. Whoops. We'll put it at the origin, because why not? No, we'll actually do a little bit above the origin. So we'll do origin is equal to vec3 z times 1.2. Yeah, sure, why not? And then we'll make the radius 4. Why not? Actually, now I think about it, we might actually want to do the underside as well. Like, just make sure that all of the sides of the sphere are actually colliding properly. So we might actually put it up quite high. Alright, what am I saying? We can just go under the ground. Yeah, let's do 1.2. So, then we'll draw it. So we'll draw scene, sphere. So we'll do sphere origin, sphere radius. We'll make it blue. Like so. So if we go into editor mode, there we go, there it is. So here's the sphere. I might actually do the whole like drawing a bit more lines, because it's a bit hard to see, like if I go from this perspective, for example, it's hard to see the surface of the sphere here, right? Because there's supposed to be a surface here. Like theoretically, but it looks like there's just nothing there. So I might just go ahead and do that just for like completeness sake, just to make this a little bit more easy to follow. Yeah, let's do it. It's pretty fun anyway. So we'll go into primitive. So then we'll have to decide how many subdivisions we want, or I guess num rings. I guess we'll do num rings. So we'll say it's 4. Yeah, 4. So sort of for each cardinal direction, we'll draw 4 rings. Yeah. So, whoops. So then the number of vertices is actually gonna be times num rings times 3. Right, so for the XY ring, we're just gonna do what for I guess J. No, let's do S. Num rings. Oops. Num rings plus S. Then we'll do float size. So the size of the ring, if we look at it in paint, of course, because why else? If we have a ring, so let's say we're drawing, rings like across this way, right? So we're gonna draw like a ring like this, and then a ring like this, and then a ring like this, and so on. Like I'm doing a terrible job, but imagine that we're drawing rings across this way. If we look at it flat on, we want to find out, okay, what's the size of this ring here? Like, what's the scale of this? Like, because this line here is obviously bigger than if we draw a ring up here. Like this ring here, this distance is obviously shorter than this distance. So how do we find the size of the ring, or the radius of the ring? So if we take half of this, this is going to be the radius we're looking for. And here's the other radius. So the radius. So how do we find that out? Well, if we take 2 examples, whoops, I went too far. Redo, please. There we go. If we take an example ring, let's take a ring that's over here. So this is the ring we're drawing. We want to find the radius here. This radius. Well, if we look from the origin, we can sort of draw a triangle here, right? We can draw a right angle triangle. We can draw, here's the hypotenuse, going straight to the edge, and then we have the going up like this. And so we can sort of see on this triangle that the radius of this smaller circle, like this semicircle on the sphere, the radius of that is the side of the triangle. But we have a very similar triangle to what we have seen millions of times before, if we're looking at like the cosine and sine functions, where this is the angle. Rather, I'm gonna draw it a little bit different. I'm gonna actually draw the radius on here, make this a little bit more, makes a little bit more sense. So these two are the same triangle, it's drawn differently. I'll actually erase this line here. So now that we've established what we want. So this is the radius here, and this is the radius just of the sphere itself. So I'll make that, yes, sure, S for sphere. And this is just the theta. So this is some angle theta, right? And this is just r. Is in this case, it's just going to be the cosine of theta times s. So this is r is equal to the cosine of theta times s. And there we have it. Of course, in this case, it's not that simple because we don't have theta. It's not that simple. We don't have theta because what we want to do is we don't want to draw like with equal spacing theta-wise. We want to draw with equal spacing, sort of cross-sectioning with the same distance from each other. Like, so we want to draw a line there, and we want to draw a line here and here. And we want the distance from these lines to be the same, so we want to sort of move them around equally. So okay, so let's say we do that. So instead of knowing theta, what we know is this distance away from the origin. We know the height of it, so we know this h. Right? So now we have this triangle. We know two sides. We know the radius here. We know the radius of the sphere. Let's just, for simplicity's sake, call it 1. So let's just say, because that is what it is. We have a sphere of radius 1. So this is gonna be 1. So we have h and we know 1. So now we want to find out what r is gonna be. And I have to think. I know one way. I'm trying to think if there's a smarter way. Because we can do it this way, right? We can say like, okay, so the side of the hypotenuse, 1, is equal to h squared plus r squared, right? Oh, sorry, the square root of this. Wait, doesn't make sense. That doesn't make any sense. No, wait, yeah. Yeah, okay, so this is this does make sense. Alright, so here we go. I haven't thought about this in a while. So let's just take a triangle, right? This is Pythagoras theorem, right? So a squared plus b squared is equal to c squared, right? Which means that the square root of a plus b squared is equal to the square root of c squared, which is of course is just equal to c, right? Because the square root of c squared is just c. So in this case c is 1, right? So the square root of a squared plus b squared is equal to the square root of 1 squared. But, okay, 1 squared is equal to 1, right? Because 1 times 1 is 1. So it's equal to the square root of 1. But of course, this, for the same reason, the square root of 1 is also just 1. So it's just 1. But another thing we can note is that, okay, so a squared plus b squared, this is supposed to equal 1. That, like, the square root of a squared plus b squared is supposed to equal 1. But if the square root of a squared plus b squared is equal to 1, that means a squared plus b squared has to equal 1 just sort of on their own. Because if the square root of it is equal to 1, then, I mean, 1 times 1 is supposed to be 1, right? So that means we can sort of we can just get rid of this square root sign, and we just end up with a squared plus b squared is equal to 1. Whoops. So that's kind of nice. So then we know a squared plus b squared is equal to 1, or in our case then it's h squared plus r squared is equal to 1. So we want to find r squared, right? So we can move one of these to one side. So we can say r squared is equal to 1 minus h squared. Right, so I'm taking minus h squared on both sides. And then we take the square root of that. So we do square root of r squared is equal to the square root of 1 minus h squared. Whoops. Alright. And of course, the square root of r squared is equal to r. So r is equal to this. I hope that makes sense. We'll just truck on. So to find the size, so the radius of this ring, so I guess I'll do ring radius. Yeah, so ring radius in this case is then going to be equal to some height. So we don't have height right now, so we'll do float ring height is equal to so the total height, the total diameter of this sphere is 2r, right? 2r. And since r is 2, oh sorry, not r, it's like 2 the radius of the sphere, which I think we call s, right? So 2s. We said that s is 1. We said that the radius of this sphere is 1, so this is going to be 2. So the diameter of this sphere is 2. So it's going to be 2 divided by num rings. But the thing that makes this a little bit more complicated is that we don't want rings at the very top and the very bottom. We don't care about that. We don't want rings there, because this is going to be points anyways. And we're going to have stuff being drawn there anyway, so we don't need a point at the top and the bottom. So what we want is to sort of evenly divide them, but we want to have a distance at the top and the bottom. So if we think about it, if we want 3 rings, for example, then we want like 1, 2, 3. So we want 1, 2, 3, 4 divisions in between them. Right? So that means that this division, this delta here, this height delta, is going to be equal to the radius, or sorry, the diameter of the sphere, so 2, divided by the number of rings plus 1. So it's going to be number of rings, I'll call it n plus 1. So we're going to divide it by 4. in this case, for 3 rings. So the ring, let's see, the ring height delta, I'll call it, is going to be 2 divided by num rings plus 1. Like so. Yeah, so to find the ring radius, so if this is the ring 0, right, we want to find the height is going to be, from the top is going to be d times, if this is I, right, so I, no wait, what did I call it, S? Yes, S. So this is S is equal to 0, like the index of the ring, right? So, sorry, if S is 0, then the height from the top of the ring, top of the sphere, is going to be d times S plus 1, right? So we want, for the 0th ring, we want 1d, so we want 1 down. And then for S is equal to 1, we want 2d, we want 1, 2 down from the top, and so on. So we'll do ring height, we'll put the ring height delta down there. So ring height is ring height delta times S plus 1. Yep. So this is from the top, right? But this formula that we made, here, is its h is from the center, right? But to get the distance from the center, so if it's up here, let's say we have a height of 0, we can't have that, but let's just do that for like sort of for example. Then the height from the center of the sphere is just going to be the radius minus that distance. So if it's 0, then it's going to be at the top. If it's 1, then it's going to be 1 minus 1, which is at the middle, which is what we expect, right? Because this is from the top of 1. That means we're at the center, because the total distance is 2. And then if it's something like 1.5, that means we're a distance of 1.5 from the top. So we're going to be like, okay, we're going to be down here somewhere, right here. So the distance from the center of that is going to be, okay, so that's going to be 1 minus 1.5, which is equal to negative 0.5, which is what we expect, right? Because we have 0.5, but it's also negative, which means we're going downwards instead of upwards. So we're sort of getting that as well for free. So the ring height is going to be this, but it's actually going to be 1 minus that. Okay. 1 minus, because we want the distance from sphere center. However, we're iterating from the top to bottom, distance-wise. Alright, so now we're doing that. So now I have the ring height, and then we'll do float ring scale is equal to the square root of 1 minus ring height. Did I do that? No, wait, it's ring height squared. We'll do A 2 plus B2 is equal to 1. So A squared is equal to 1 minus B squared, which means A is equal to the square root of 1 minus B squared. Alright, so then when we're making the rings, we'll use times that by ring scale. Yep, and then we'll position it with ring height. On the z-axis. So let's see what we get. Ta-da! So it kind of worked. What's interesting though, it says it's actually not touching. So I might have made a mistake. How many rings did I do? 4. Let's do 3 instead. Or let's do 5. Just so we have an uneven number. Yeah, I've definitely made a mistake somewhere. So here you can see that clearly these two should be touching, right? But they are not. So why is that? Interesting. Or I've done the height wrong, because it kind of looks like they're not even in a space even. Like, see here, this distance up, if I sort of go away a little bit. I think the problem is the spacing, honestly, because these two are clearly further away than these two. So I've clearly made a mistake there. Alright, I'm scaling the whole thing by ring scale, that's why. So the problem is that ring height... I'm scaling this whole vector with ring scale, which means that the ring height is also going to get scaled. But what we just want to scale is just how wide the radius of the circle. We don't want to scale how far up and down it's also moving. So unfortunately we're going to have to do this, which is kind of ugly. Whoops. Like so. So now if you look, that looks better. So now it looks like we have something actually resembling more of a sphere. Pretty dope. So I wonder if I want to do this. It is going to get a bit messy, the code, so I might just do a little bit of refactoring. So we'll do build ring, sphere ring. And we'll do like 3 verts. Whoops. And we'll do float. Now we might just do sphere rings. So we'll do like 3 axis A and 3 axis B. So then we'll just copy this. So we're gonna provide which 2 cardinal axes this ring is gonna lie on, right? So right now we've been doing the XY plane, right? So these rings are lying on the XY plane, right? But we're gonna make rings in this direction and also in this direction here, and also in this direction here. So we're gonna make rings all the way. So then it will actually become like a almost like a curvy, what do you call it, like a NURBS mesh, I think is what it's called, or something like that. I don't actually know. I'm not a graphics person, but it will become like faces that we can actually see. But we have to do it for each of the cardinal axes or cardinal planes. But right now we'll only do it for the XY plane. So let's see. We're looping through all the rings. Ring height's gonna be this. This is still correct, but then we'll do something else. We'll do like 3 cross. We'll do plane normal. It's gonna be just cross axis A and axis B. So then this is, instead of doing this hard-coded things, we're gonna do axis A times cos of angle plus axis B times cos of angle. Not cos, sine. And this is gonna be timed by ring scale. And then we're gonna add plane normal times ring height. So there we go. So now instead of making this sort of hard-coded like x, y thing, we actually do like, okay, x, and if this is x and y, so it would be like x times the cosine plus y times the sine times ring scale. So we're scaling down only the ring part, like on the cardinal directions, but then we're also adding the plane normal times ring height. So we're moving it up on the normal, so that will be the z-axis in this case. We're moving it on the normal up and down with the ring height, so that won't get scaled. And what's good about this is that this will work for any two axes. We can just provide any two and they will always work, which is nice. So axis A times the cosine of angle next plus axis B, oops, times the sine of angle next times ring scale plus, whoops, I am messing up, times ring scale plus plane normal times ring height. There we go. Alright, numberings is not defined up here. Whoops. Numberings and ring height delta, like so. That const. Right, so we'll do ring resolution. We'll move all of that stuff up here. We might have to, yeah, we might have to make this actually outside of here. Whoops. So we'll do sphere ring resolution and sphere numberings. Like so. I will also do it will return how many vertices actually made. So we'll do an offset here, set it to 0, and then we'll plus it, and then we'll return the offset. So we'll also return like how many vertices did it actually like put onto the thing. Great. But does it work? Is the question. So we'll try with XY. So we'll do, let's see, build sphere rings. So verts will just be verts, and then we'll do axis A is going to be vec3x and vec3y, and that's going to be it. And then it's going to return how many vertices it made. So then we'll do offset plus equals both sphere rings. Yo, what's up, Manusbox? How you doing? Hope you're doing swell. Welcome to fucking math hell right now. We're just doing some sphere stuff. And then we can go back to the juicy collision stuff. Right, so now we have to do sphere ring resolution and sphere numberings. I renamed these. Maybe? No? Alright. Maybe? Let's see if it works. And boom. I think it works. Yeah, it looks good. Alright, so we have what we had before. So we have the rings. So we have like the three cardinal rings, like here, here, and the middle one. But then we also have these sort of subdivided rings in one of the cardinal planes. So we have like the XY plane. So now we want to make it for the XZ plane and the YZ plane as well. So hopefully this just kind of works. And if it doesn't, then, well, then, you know, that's just how life is, you know. So we'll do on the XZ plane and on the YZ plane. Whoops. Alright, okay, so this is not gonna work. Yeah, okay, yeah, so this is what I expected. So, I made one mistake. The mistake is that we have this function, build sphere rings, and it takes a pointer to a vec3 array, right? And it sort of builds into the array, builds the vertices, right? So it keeps like traversing through the array, building the vertices for one group of rings, for one like cardinal plane. Maybe I should have done plane normal. It doesn't matter. Right, so it does that, but the problem is this verts, I send in the same pointer all the time, right? So I send in verts, and then I send in verts again, and then I send in verts again, without offsetting it. But of course I want to do like, the first chunk is the XY plane, and then the second chunk, like after those vertices, I want to do the XZ plane, XZ rings, and then I want to do the YZ rings. So I of course have to do plus offset here. This is going to return how many vertices it builds here, so that's like I have this offset variable, and it's going to return, this build sphere rings is going to return how many vertices is built, so then I have to offset the array by that much to keep building the next set of vertices. And now, ta-da! We have this nightmare. Doesn't look quite as good as I hoped it would, but you know what? I'll take it. I will take it. So this is our debug sphere. Maybe if I remove one of the cardinal, it will look better. Probably not. It's probably still look whack, right? If I remove the YZ, for example. Yeah. You know what? Good enough for me. I think the way we would have done it actually, if we were like super good and not like whack, is what we would probably have done subdivisions on one axis, like subdivisions on the z-axis, doing the rings we did now. But then on another axis we do like a rotated thing. It's like, so we do, what we probably should have done is do like rings on one axis like this, and on the other axis we do rotated rings. We do like that, and then like this, and like this. So then we will get more of this, this nightmare. But I'll take it. You know what? It doesn't matter. This is just a debug sphere anyways, so it doesn't matter. And I feel like this is close enough to giving us sort of what we're looking for. So now we want to rate test against this sphere. But first, before we do that, I'm very hungry, so I'm just gonna go grab a quick snack. So, hold on, I'm actually gonna put up a message for it as well. This is not the right message though. Grabbing food. BRB. There we go. So, be right back. All right. Let's continue on. So, right, so we have this ray here, this green ray, and we want to check this against this blue circle. Sphere, sorry. So let's do that. So we have this test ray sphere function. And test the collision of a ray and a sphere. Pretty simple stuff. And then we will so we will do hit. Whoops. Hit is equal to test ray sphere. So the ray and sphere. And if hit has hit, then we'll do these things. Vi får åka dina kodkonstapper in Dota MMR väldigt mycket. Very much. Dota is like playing coding is like playing a game of Dota. Okay, so right. So okay, so now we're testing the section and we're drawing it out if we get a hit, but of course we don't have a hit because we're just returning we're just returning an empty hit result. We don't have any code for actually checking a hit. So how do you test a sphere? How do you test a sphere line intersection? Is that blue outline a blast zone from a grenade? It could be. It could be. If I had grenades, then for sure it would be like, you know, some sort of sphere detection to check what is hitting, and these dudes will totally get hit. God, it looks so bad from this angle. I hate this sprite. Why did I make it? Why did I make you? I hate you! Okay, anyways. So, let's check it out, yo. So we have a sphere. Right here. With some location. Some origin. Let's call it S. Yeah, let's call it S. So is the retropixelation effect a shader or just a low res frame buffer? It's just a low res frame buffer. So that's why it looks kind of whack sometimes. Like especially when I'm drawing sprites, you can definitely see if I go into like actual game mode, you can sort of see that the sprites are very jiggly, like they're very boily. They look like they're boiling, and also the health bars are sort of going in and out of phase of being in a integer amount of pixels. So all of that is sort of stuff I'm gonna have to take into account at some point. But yeah, it's just I'm just drawing on a scaled down frame buffer and then scaling it up. Just gonna kill these guys. Yeah, you two fight each other. What? He shot through the dude! Cheating. Oh well, whatever. Right, okay, we were doing math. Okay, so we have a sphere. And a sphere has some radius. Some radius are. All good stuff we know and love. And then we have an array. Array has some origin, and then it has some direction to it. I hope you guys remember this from like 1.5 years ago, when I had you guys in school. So let's first do the case where they don't intersect, just to sort of see what the steps are. So first of all, we want to find the closest point on the line. So if we take this span, like the ray span, and we want to find the closest point on the ray span to the sphere. So to do that, we just project the sphere's position onto the ray, like this, to find this. So this will be the closest point, I'll call it C. Freeman is raiding with a party of 30. Oh dear. Hello, everyone. We're doing math. Look, it's a sphere. Hello, everyone. Oh no, I'm getting raided. Oh no. Look. Guys, I hope you like math, because we're doing hella math right now. Look, here's the game. The game is like... Oh no, this is so... Here's like a sphere. Look, here it's a sphere. It's a ball, and we have a line. Look, and we want the line to hit the sphere. And there we go. And that's what we're doing. Yeah, so I'm just building what we're in the process of doing right now is we're building a collision library for the engine as I call it, for a game that I'm making. Maybe we could put some music to make the stream warmer. Well, have music on. Is the music not showing up? I should have music on. Wait, is the message still up? Oh no. Oh, okay, thank you for that. I will bump it up a little bit. Let's get some bumping music up in this. There we go. I'm quite new to streaming, so mistakes will be made. Alright, so okay, we have line plane intersection like this, so we can get like the hit of a line hitting a plane from the upside and the downside. That's what we did just a while back. So now we want to move on. Like, that was fucking baby mode. Now we're going into like hyperspace fucking collision checking. Wanna this thing with this thing. How is that gonna work? All right. So now it's time to math it up. So okay. So we want to find the closest point on the ray span to the sphere, right? So we want to find the closest point. And to do that, we want to project the sphere's position onto the ray span. Alright, we did this before, up here, like, dear God, this was a mess. So let's just forget about that for a second. That was old. So what we want to do is we want to take the vector from the ray's origin. Oh, I love this music. This is what's happening in my brain every time I do math. So we want to take the vector from the origin of the ray to the sphere's position, right? So I'm gonna take this vector here, and that's gonna be s. Where's my mouse? There it is. So that's gonna be s minus o. Like this music is making me feel things. All right, so we get s minus o, which is gonna be the vector from the origin of the ray to the sphere, and then we wanna project that vector. Onto the ray. So to do that, we just take this vector, we dot that bad boy with the direction. We dot these two. There we go. We dot these two, that gives us the length of the projection. That's gonna be the length here. I'll make an L. Yeah, L. That seems good. So L is gonna be this. And then to get the point, the actual projected vector, we take the origin plus the direction of the ray times this length here times L. Isn't that magical? Look. With math, anything is possible, and that's gonna be equal to C. Alright. So it's fine if this doesn't make total sense. It's like, this is the way it is. So that's gonna equal to C. That's gonna be our closest point on the ray to the sphere, right? Fantastic. Then what? Fucking then what? Well, then we can just get... Okay, what's the distance? Where's my mouse? There it is. What's the distance from C to S? So what's this distance here? I'll call that D. So what's the distance from the sphere to the closest point on the ray? What's that distance? Well, that's just gonna be the length. I've reused the H. Hang with me here. So it's gonna be H. I'm currently learning the Ka framework using the Hax language. I know the Hax language. That's the language that Dead Cells is made with, right? I feel like I've heard of that before. That's whoa. Dead Cells Hax. Yeah. That's sick. I've never seen hacks in my life. So that's cool. Like I feel like learning new things is always super sweet. My mind's already blown, maybe I should go to sleep. Dude, this is where the action happens, okay? We gotta get through the beautiful math. And then shit's gonna get crazy. I swear. Your mind is gonna be double blown. Thank you, Trulkrov. Have a nice day. Have a nice evening. All right, so we're almost there. So H is gonna be. Whoops. Double. I'm not gonna say that out loud. I'm not even gonna honor you with a mention. So H is gonna be C minus S. And it's gonna be the length of that. Oh, okay, this is my mind. You know what? I was thinking something else. I was thinking something inappropriate. That's a me though. That's a me though. You're a good boy. So H is equal to C minus S. That's the vector between the sphere and the closest point. And we take the length of that. Magic! Through mathematics, we achieve greatness. Let's code this. I'll just close everything else. This is what we're doing. We're doing hit tests. We don't need anything else. Alright, so we have nothing. We need this. Okay, so how do we do this? What steps do we take to do this? Okay, so can I like always on top this? No, I can't. Okay. First step, getting the closest point. Alright. We want the C, right? So, to get C, first of all we gotta get L. Alright, so L is the first goal here. So float, I guess we'll do closest point time is what we'll call it. So time is generally what I call a distance along some ray. Like, so you say like a time of 1 means a distance of L traveled along the ray. So, and that's what we want, right? We want the distance along the ray to the closest point. And that's gonna be D, that's the direction, right? Dot the vector from the origin of the ray to the sphere. So first of all we'll do ray to sphere. That's gonna be equal to sphere origin minus ray origin. Then at closest point time, it's gonna be, excuse me, it's gonna be dot ray to sphere and ray direction. Alright, whoops. And now now that we have the closest point on time, we can get the closest point just like on its own. So that's gonna be ray origin plus the ray direction times, whoops, closest point time. So we're just traveling along the ray. It's traveling along the ray for closest point time units, and then we'll reach the closest point. Linuxidable. I'm sorry, I can't pronounce your. Okay, are you using a framework library like SFML, STL, or are you your engine directly with DirectX OpenGL Vulkan? I am doing directly with OpenGL, with nothing on top of it. I'm trying to use no libraries, nothing external at all. I'm trying to write everything from scratch, just because I feel like I want to do it at least once in my life. So stuff like context creations, instead of doing using something like SFML, I just use WinAPI raw to do that stuff. Which, you know, it was a nightmare to do, but once everything is at place, at least I don't have to touch it. And also stuff like the bindings. So here are all the function bindings to OpenGL, and I decided to, instead of using glue to wrap all the functions, I used do it myself. But this wasn't that hard, to be honest. It was just like, you know, getting all the functions and importing them. But yeah, so I'm trying to do everything from scratch. Sort of the goal of this project, which is why I'm doing collision from scratch as well, instead of using some nice, neat library that's probably out there. Yes, so the closest point is gonna be traveling along the ray. Traveling along the ray for closest point time. Are you sneaking autumn leaves into a programming Steam? You fucking know it, dude. There's always time for autumn leaves. Alright, closest point. Yes. So we have that. Okay, so now we have the closest point, and now we want to get the distance. So we get distance to sphere is going to be equal to closest point minus sphere origin. Whoops, origin. And it's going to be the length of that. You might just want to do the length squared, because we don't care about... No, you know what, we're gonna care in a bit, so okay, never mind. I didn't say anything. Nothing happened. You can't rewind the stream, you can't check that I did wrong. Yeah, okay, so to check if we're hitting or not, we'll just do... If the distance to the sphere is less than the radius of the sphere, that means that we are inside of the sphere, right? The closest point on the ray is closer than the radius of the sphere. So by definition, the closest point is closer to the sphere's origin than the edge of the sphere, which means we are inside of it. So we'll just do the opposite. If distance to sphere is greater than sphere radius, oh god, I don't know what that was. So if distance to sphere, let's just hope that doesn't happen again. If the sphere is greater than sphere radius, it's some sort of snippet or something. If it's greater than radius, then we just return an empty hit result. We say like, okay, we're outside, the closest point of the ray is outside of the sphere, there's no way we're intersecting. Yes, okay, so now we're early out in that case. I'll actually, you know what I'm gonna do. If the closest point is further away than the radius, we are clearly not intersecting. Right, and then otherwise I'll just do return hit make. We'll make like a temporary one for now. There is a few things we need to do more, but just to get some results up and running, we'll just return like the closest point as the intersection point. So we'll do hit make. Position is gonna be the closest point. That's not correct, but it's fine. Normal is gonna be something else as well. We can just do... Let's just do ray direction, like the negative of the ray direction for now. Doesn't matter. Time is then gonna be closest point time, like so. Alright, let's check it out. So I'll go into editor mode. Excuse me. Oh. And bring up the ray. Ciao! And then I'll start intersecting the sphere. And we can see that we are intersecting. So the closest point is here, so that's the closest point to the origin. And right now the normal is just pointing like back towards the ray origin, so that's fine. We're gonna calculate that in a bit. But the important thing to note is that, okay, when we're actually intersecting, it's saying we're intersecting, and when we're not intersecting, it's saying we aren't. So right now we're like hovering right above the sphere, so we're not getting an intersection, but if I move it just slightly inwards, then it's saying we're getting an intersection. So at least now we have the test working, like it's giving us a true or false, and that true or false is correct. Now it's time to do the other things, which is figuring out what is the actual intersection point, like where, because that's supposed to be here, right? That's the first point where we're entering the sphere. That's what we want to find out, because if like a bullet is coming and a bullet is hitting the sphere, we want to find out where did you hit the sphere and what was the normal, so that we can maybe like bounce off or make it spawn some effect or something where we actually hit it, in case the sphere is like a dude or something. I'm wondering if I should maybe remove spawning. Nah, they can move around, it's fine. They're not in the way. Yeah, okay. So, how do we find that out? So let's redraw this a little bit and draw the actual scenario we're looking for right now. Which is like a line going like this. Bam, boom. Here's the origin. And here's the closest point. Bang, there. So this is a scenario we're having right now. Very sweet. So, we want to find this point here, right? This is the point where it's actually intersecting the circle. Correct? The circle, I'm saying circle, I mean sphere. So if I draw a line from there to the origin, I missed it. If I draw a line from here to the origin, right there, we have a right angle triangle, right? Since the closest point, sort of by definition, is a right angle to the line itself, we know we will always have a right angle triangle. And the dope thing about this triangle is that we know two of the sides. We know this side here, that's the closest distance, right? So that's, what do we call it? H? Yeah, we call it H. So that's the closest distance. We know this side. And this side here, since it's going from the origin of the sphere to the edge, right? It's going to the edge where the intersection happened. We know this line is just the size of the sphere. This is the radius of the sphere. So we know two of the sides. So we're trying to find this penetration depth, right? So we call it P for penetration. So we have a right angle triangle looking like this. So we have H, this is this side, we have H, we have R, which is the hypotenuse, and we have P down here. And with our friend Pythagoras, we can say that P squared plus H squared is equal to R squared, right? Fantastic. We want to get P, we want P. It's a weird sentence to say. So I'll just move over H to the other side. So we'll just do P squared is equal to R squared minus H squared, right? I'm just minusing H squared on both sides. So then we have this equation, and then we can just square root both sides. So the square root of P squared is equal to R squared minus H squared square root, like that. Which means that P, since like the square root of P squared is just going to be P, so then we have P is equal to the square root of R squared minus H squared. Fantastic. Through Pythagoras, we achieve hope. So now I'm actually seeing we might actually want this in square. Yeah, we might actually, you know what? I was wrong in being wrong. We want this as a squared. So I'll just do length squared in this one. So we'll do distance to square, distance to sphere squared. And then we also want the radius squared. So we'll do square, sphere radius. Perfect. So then we'll just check the square here instead. So we'll do radius squared. And the good thing about squaring distances is that differences, like in terms of comparisons, like one distance being bigger than the other, does not change when you square them. So the square of a distance will have the same comparison to another square distance, no matter if you square or square root and so on. So this will still be true. And now we need to find the penetration depth, and that's then is then going to be equal to the square root of radius minus h, which is the closest distance. So it's going to be radius squared minus distance to sphere squared. Yes. So now we can find the actual penetration point. So we'll do penetration point is equal to ray origin plus ray direction times closest point time minus penetration depth. Right? Because we're just taking this time here, right? So this is like the time that we had before, like the distance to the closest point on the ray to the sphere. This is t. We're taking t and then use minus p, right? We're going back the penetration depth. We're like taking that away, bang. So then we'll end up here. So this is going to be t minus p. And then we're saying that's the actual time it took to penetrate, or sorry, to intersect the sphere. Good. So we'll do closest point time minus penetration depth, and that's that. I guess we'll do intersection time. We'll write it out. Like so. So we'll do intersection time. And then closest point, instead of this, we're gonna have penetration point. There we go. Whoops! Yikes. And then here it's gonna be intersection time. Like so. And now if we check it out, check it out, bang, and we have our proper intersection point here. This looks pretty proper to me. Right there, right on the sphere. Perfect. So now the normal is incorrect, right? The normal is pointing downwards, but the normal in this case is supposed to be the normal of the sphere, right? We're expecting the impact, the normal of the surface that we intersected with the ray. So to find the normal, well, that's pretty easy, right? The normal of the sphere is just the direct vector from that point, from the origin to the point, right? The normal of the sphere is always just gonna be that point's position from the origin, right? Like it's just gonna be this straight line. It's always true that that's gonna be just the normal of the sphere, no matter where on the sphere we are. So to get the normal is quite easy. We just do vec3 normal. I guess we'll do penetration normal. Let's not call this. Let's call it intersection point instead. And the normal is just gonna be the intersection point minus the sphere origin. Oops. Origin, and we'll just normalize that. Whoops. Like so. So intersection point minus sphere origin will just give us the direction, or the vector from the sphere origin to the intersection point, and then we just normalize that, so we get a unit vector, and that's gonna be our intersection normal. Intersection normal. Oh, whoops. And if we go and try it out, now that's a normal that I'm expecting. So now we can see that the normal intersection point is like on the sphere, which is what we're expecting. Even though it's going through the sphere, we're getting like the first point of in contact, and the normal is pointing just outwards from the sphere, no matter where we're hitting it. Fantastic. So we have a couple of bugs though. There are some things that are not going to work right now. The first one is if I look away, like you might recognize this bug. If I look away like this way, we'll see that it thinks it has an intersection point here. Like it thinks it's... First of all, it thinks it's intersecting at all, which is of course a bug. But it also thinks that the intersection point is on the other side of the sphere. So we have like a double bogey of incorrectness. But of course this is happening for the same reason it was happening with the plane, is that we don't care if the time that we're getting, this time here, we don't care if it's positive or negative. So we don't care if we have to travel forwards or backwards on the ray line to get to the closest point, alright? So that's sort of the bug we're having. But of course, as an emperor of my engine, I'm just gonna say that rays can only intersect forwards. They cannot intersect backwards. Ray is one directional and they don't go backwards. I'm just gonna say that. Like, that's what I'm deciding. It's not correct or incorrect. It's just sort of what you're defining it to be. Alright? And I'm gonna define my ray to be it can only go forwards. So if you just do if closest point time, whoops, is less than 0, I'm saying, okay, that means the closest point is behind us, so you just get out. So you just do return, whoops, return hit results. Return nothing, return empty hit results. Oh, whoa, health bar. So if I go here, and I look away, oh wait, there we go, moving the ray, there we go. Then we see that, okay, it would be intersecting like backwards if you look at it, it's like it's sort of pointing away from it, but we're not getting anything. So that's good, we fixed that. So I'll just write, don't intersect if the closest point is behind us. Great. However, there is one case where we do care, where we do say like, okay, it's fine that it's behind us, and that's a little bit more of a tricky case. That's this case. If I'm inside the sphere, if the ray starts from inside the sphere, we are expecting it to intersect, like, right? Because we're sort of expecting that this is the first intersection point. Right now we're sort of starting penetrating, right? We're sort of starting from inside of it. But we're assuming that the sphere is a solid object. We're assuming solid spheres, not shells, right? So you might say, okay, the intersection point is here, right? That would be true if it's a sphere, if it's a shell. If it's a shell of a sphere, that means it's empty space inside, we're going out and hitting the shell, right? But I want to assume that it's a solid mass, it's a solid block of stuff. And that means, as we're starting the trace, or the ray thing, the ray intersection test, it immediately hits something. It's like, I started and I am inside of the sphere, I hit something immediately, I'm like sort of stuck inside of this. And you will sort of you will usually call that a start penetrating problem. So we say like, okay, you did a trace, but the trace was start penetrating, which means it was already inside of something. So that's makes some things a bit more complicated. That means the normal will sort of not really make that much sense. You might have troubles. You might have to depenetrate something, like if you're doing movement, for example, and something's stuck in a wall, you don't want to handle it like it's like it ran into the wall. You actually want to say like, okay, we're started penetrating, we gotta get him out of the wall. So this is a separate case that's important to note. I'm not gonna care right now. I'm not gonna do T penetration quite yet. I'm just gonna say like this is valid. Is this regular old hit result? Just return as if we're intersecting here. So we're gonna have a position here, and we're gonna have the normal be the same as before. The normal is gonna be from the origin to the intersection point. All right. So let's see. We have the ray to sphere. Oh yeah, of course. And how do we detect this? Okay, so we should probably start there. How do we detect if this is happening? Well, it's happening if the origin of the ray is inside the sphere. All right. So if we have the ray here, right? All we have to sort of do is to check. Okay, distance from the sphere origin to the ray origin. Is that distance less than the radius of the sphere? All right. And if it is, that means the origin of the ray is inside of the sphere, and then we do this sort of edge case handling. Whoops, I flipped my mouse over. So we'll just do if. I'll just move radius squared up here. So if length squared of ray to sphere is less than radius squared. Again, it doesn't matter if they're squared or not. The concept is the same. I'm comparing the lengths, right? It's just that when I'm comparing the lengths sort of by binary like this, like is it less or more, you know, then it doesn't matter if they're squared or not. So just from a computational, just from a, I guess, an optimization standpoint, it's better to use squared, but it doesn't really matter that much. So right, okay. So if the distance from ray to sphere is less than the radius squared, then we say okay, you've immediately started penetrating. Ray origin, whoops. Ray origin is inside the sphere. We have started. We have start penetrating scenario. So then we'll just immediately return a hit make, and the point, like the point of the hit, is going to be the ray origin. The normal is going to be we have ray to sphere. So the ray to sphere is going to be the other way around, right? It's not going to be this arrow, it's going to be like this arrow. So it's going to be the opposite of that, right? Because that's pointing into the sphere, but we want it to point out of the sphere. So we'll just flip it. So we'll use the minus, ray to sphere, and then we'll normalize it. Like so. And then time is going to be 0. So it's like we immediately hit 0 time. Like we didn't go anywhere. Let's see what happens. Okay, so oh yeah, it's because it's inside there. Okay, so there we go. So right now, okay, this is still working. We're just looking down and we're sort of hitting the ground. And if I look away, we're not getting an intersection, a backwards intersection. I might be missing it actually. Let's go down here like that. Okay, so we're not getting a backwards intersection, but if I back into it, if I look inside here and look out like this, let's just do it here, then that works. So we're getting an intersection immediately at the start of the ray pointing outwards of the sphere. Fantastic. Great. So that's working. That's working is fine. I would say that's I can't think of any more edge cases at least. So, what's the next step? Right, okay. So now we've done this with lines, or sorry, with rays. Okay, we've done this with rays. However, there is another type of sort of ray trace, or I guess a ray, which is just a line. Okay. So a line sort of mathematically is this infinite thing, right? It has 2 points. It has 2 points. So it's 2 points, and the line is connecting the 2 points, and then sort of continuing out infinitely in all directions. So very similar to our array, right? I'm saying it's, I guess it starts at a point, so I guess we will cap it here, right? So it starts at a point and then goes away, goes infinitely in another direction. However, I want my line in my engine. Excuse me. And again, this is just an arbitrary decision, right? We're making a decision about what we want these things to mean. And I'm making the decision that I want a line in my engine to be 2 points, 2 points in world space, and a line connecting the 2 points. Exactly. It doesn't go past the points, it connects them only. Right? So it connects the 2 points and then stops there. And the important thing about this is that this is different from array, right? Because an array, I'm saying, intersects anywhere, like infinitely forward. It can intersect at any point. But I want the line to be only intersect if we're intersecting within this distance. Like, so if we have array at this angle here, right? It would intersect the sphere, right here. But if we have a line that starts here and ends here, then we're saying, no, there was no intersection. It did not intersect, because it didn't reach the sphere. And this is important, I think, since bullets, for example, or everything that's moving, really, and doing some sort of line intersection check, like a projectile moving, and it's want to say, like, okay, moving from here to my next point, this frame, is there anything in between there that I'm hitting? I don't want to check infinitely forward if it's hitting something. I don't really care if it's hitting something in 5 minutes. I just want to know this frame didn't hit anything. So then it's important to do this sort of capping, right? I want to cap the line. So so how do we do this? So I have my collision types here, so I have the line here. I've already made it. So a line is just a start and an end. Again, the 2 points. The 2 points to connect with the line. I want the line to only intersect if we have array. It would intersect the sphere. If it can't reach the sphere, then no. For bullets, for example, moving from here to the next point in between, it would check if there's anything in between it. So if, for example, if I have this line that goes from point to there, is that what I said? Is that like what I said? If we only intersect this point, the ray. Yeah, but I think what you're saying is correct. Like, especially, it's a lot of parts. But there was one thing you said where it's like you check the ray, and then you check like sort of if the distance that you hit was too far away, right? Am I getting your points correctly? Something like that, right? I just use machine learning to complete what you say. What? What the hell am I reading? Oh, is it like the article complete thing? What did you paste in? What did you what did you write? Because I was kind of rambling, so I was like, is this me? Is this me rambling? I should have made a script. But yeah, you know what? I'll give credit to the GTP2 GPT-2 model. It's making me think things. But alright, so anyways, to go this next step, to go from a ray intersecting a sphere to a line intersecting a sphere, what we want to do is that we want to do the same intersection test. Do the same intersection test as we do with the ray. But then we want to find out the intersection, did it happen at a point that is too far away, like that's too far from the line end to matter to us. Yeah, I'm quite amazed by machine learning. I think it's super fucking interesting. I want to do machine learning someday. I should really sit down and like learn what it is and write something cool. Because I feel like it's sort of things where it's like you sort of experiment. You're like, oh, I'm gonna try this weird thing, and then it's like you don't know what's gonna come out of it. It's sort of chaotic in that way, which is very interesting. So let's start with a line sphere intersection. Alright. Line sphere. So we just want to do the same as with the ray. We could copy all of this if we wanted to, which is probably the most efficient way to do it, honestly, but let's do it simply first, and then if I need to make it more efficient, then I'll do it later. So first we'll construct a ray. So we'll construct a ray that sort of represents the line for now. So we'll do float line length is equal to line and minus line start. We'll do line length squared actually. Right, so we're just getting the length squared of the line. And then we're gonna construct a ray that's aligned with the line. So we'll do line ray. So the line ray origin is gonna be at the start of the line, and the line ray direction is gonna be just normalize. Oops, normalize. Oh wait, I have a fucking function for this. I have oh yeah, I have ray from 2. I remember I made a function to make a ray just from 2 points, connecting 2 points. So that's gonna be line from and line 2. How convenient. And then we'll just do the hits checking. We'll do the collision checking. So we'll do get a ray hit is equal to test ray sphere. Like so. And then we'll check, okay, the time of this hit, like the actual time it took to hit to intersect with the sphere, is that longer than the length of the line? And if it is, that means disregard this. We may have hit it in an array world, but since our line is not infinite, it's finite, it was outside of the length of the line. It's outside of our finite existence. So we'll do if ray hit time is bigger than, I will do square as well. So if the square of the ray hit time is bigger than line length squared, then we say disregard this. Otherwise, return just the ray hit. Like so. There we go. So we can do the same thing with line plane. So the same thing will apply here. We just do the ray plane intersection and check if the time was within the line bounds. So we'll just do the same thing. So we'll do ray test ray plane. Oh, whoops! I didn't rename this. Like so. Oi oi. All right, it's start and end. Right, it's not from and to. Ened. There we go. Oh yeah, and then we have to actually use it as well. So we'll go into editor. And now instead of array, we're gonna do a... I guess we can keep it as array and then just convert it to a line. So we'll do convert array to line. So we'll do a line is equal to, let's see, start is array origin. And then we'll make it some length. We'll make it 5 units long. So not quite short, quite short. So then I hopefully we'll see more when it's actually missing because it's too short. So we'll do that, and then we can draw the line from just line start and line end. And same thing here. We're gonna do test line sphere, like so. And let's try it. So now if it are, yeah, there we go. So now the line is 5 units long. All right. We can sort of measure with these these things here maybe. So we put it like there maybe. See, okay, it goes from halfway. Then 1, 2, 3, 4, 5. Yeah. So it's 5 units long. Great. So now if I'm more than 5 units upwards, I can sort of just miss it, right? So then, see, it's hovering above the plane here. So then we consider that, okay, it's missed. Great. And then the same thing with the sphere. Now I'm too far away, so it's missing the sphere. But then if I go a little bit closer, there we go. So now it's intersecting the sphere. Great. So we're done. That's about it. So let's push this before I forget. Whoops. Fucking suck. Alright, so now we have that, and I'm gonna go ahead and remove the old ones I had. Which were these ones. So these were the old intersection tests I used for what I had, like going into this. I will remove this file completely actually. So let's see, core math. Let's see, core math, and then here we'll remove this. Bye bye. I don't need you anymore. Close this. There we go. So now we got a bunch of errors, so that's fine. So now instead of, let's see here, so this is returning arrays here when we get the mouse array and stuff. So instead of let's see, instead of including math array, we want to include core collision types, like so. Wait, is that not it? It might be an editor actually. Yeah, it's in engine. There we go. Great. And then we will see here. So we have these tests here. Yeah. So we should probably do... Maybe we should actually do some... I was thinking if we should do some helper. Nah, it's fine. Okay, so let's see here. Honestly, I don't care about this one. Let's just get rid of this one. Where's this camera? Okay, so this is where the camera is checking where we're aiming. I would not need this either, to be honest, because I've saved it on the player nowadays. So we could probably just do game. Where's aim location? Yes, aim position. Alright, that's... Great. So where are we now? Projectile. Okay, so this is where things get sort of interesting. So here's the projectile. So now we want to make remove this, and we're going to make a sphere. So that sphere is going to be the unit sphere. So the unit sphere, its origin will be at the unit's position. So this is where a projectile is checking collision with units, and the radius will be 1. Maybe 0.5 actually. Intersect time we don't have anymore, and then we'll do a hit result to be the unit hit. And that's gonna be a test ray sphere. So ray is gonna be move ray. No, it's not gonna be a ray anymore, it's gonna be a line actually. Right, so this is wrong. So we'll do a line, move line. Because now we actually have that. So the start's gonna be click 3, projectile, position, move line, and it's gonna be, now we actually can maybe do it at the actual position of the line. So we'll do, it's gonna be vec 3, projectile, whoops, move line, start, plus projectile, whoops, direction, 0 times its movement speed. Yeah, I can probably do this to save a little bit. Yeah, this will probably be better. Like so. Oops. Alright, so now we have the line. So now we can do tests, line, whoops, sphere. So we move line and unit sphere. And then we'll just check if unit hit. Let's remove all of this. If unit hit has hit, then we don't need to do this check anymore because we do it in the actual thing. We don't need to do this either because we can sort of set the projectile position to be in the unit hit position. So where we hit it. And I want to actually try something. Now that we have this... No, okay, I'll make it work first. So let's just do this. Great, that's fantastic. Yeah, this is obviously like 2. Alright, we're going to include the testing. What do I call it? Hit test, alright. Like so, we're including it. Still have a bunch of errors. Now it's going to be equal, and it's going to be that vec 2. I'm probably going to make the projectiles be in vector 3 soon, because I feel like that's gonna be cooler for this. Alright, done with that, and then we have... Okay, so here we're doing the aim position stuff, so then we'll do a hit results for mouse hit, or a ground hit, I guess. We'll do plane, ground, plane. Like so. Right, we don't need this anymore. Okay, let's do player aim position. We did the ray test twice there. Alright, and let's see what happens. So I can aim and I can shoot. And I'm hoping the bullets... Oh, okay, so the bullets don't hit units anymore. So that's not good. Looks like they're on the same plane and everything. So it just looks like it's kinda just going through. Oh yeah, I know what it is actually. Yeah, okay, yeah. So the problem is that if we go back to the projectile, I made the sphere be at the origin at height 0. So at the feet of them. But of course I want it to be at their belly, so that the radius covers the head and the feet. So this should be at 0.5. So now if we go in and we sort of... It's kind of interesting to see the bullets like go off in the distance. Okay, so now we can hit them. Okay, cool. So everything's going just dandy. So something I want to try now that we sort of... Now that we have this sort of interesting values in the hit result. You know, stuff like the normal, the hit normal and stuff like that. We can actually maybe do some more interesting things. Sorry. There we go. We can perhaps do a bit more interesting things. Like, for example, have the projectile bounce off it. So, like, the projectile is going to hit the thing, and it's going to bounce off it. So let's do that. So let's do, first of all, we need some sort of reflection function. So let's do that. So we'll do a inline vec2 reflect. And of course a reflect, so it's going to have a vector, it's going to be a normal. Reflection normal. So it's going to be, let's see here, so it's going to be, vec2 projected vec is going to be constrain to direction. Reflection normal. Oops. So it's going to be the projected vector. So constraint to direction just projects a vector onto a normal. So we have that, and then return is vec minus projected vec times 2. So that's the reflection algorithm, or I guess it's called. I guess it is an algorithm. So we have these to make a vec 3 and a vec 4 version. I don't actually know if it makes sense to reflect the vec 4 vector. I haven't really thought about it, but like so. Oh, we don't have that for vector force. Okay, you know what? Maybe it doesn't make sense to make reflect vector 4 vectors. So let's use not. Alright, so now we have that. So then what I want to do is that when you hit something, so hit unit, instead of hitting and destroying itself, which I do here, what I actually want to do instead is just... oh, I will do what I break though. Is what I want to do is I want to do projectile direction. Your code style seems heavily inspired by John Blow. I am inspired by him, I think. I like his way of thinking. And I like his way of just structuring, I guess, structuring code. So this project has been a little bit of a challenge for me to structure it more in that way. I've been sort of... I guess I've sort of painted myself into object-oriented corner lately, where everything I do sort of becomes very complex, it becomes super complicated very quickly, and I try to think about solving all problems instead of solving the problems I have. So this project has been more focusing on what problems do I have now and how do I solve them, and with additional quirk of doing more, you know, data-oriented, no object-oriented style. Which is not, I'm not saying it's better. It's not better, but it is what I want to try out. Like, I will not poo-poo anyone who does object-oriented, for sure. Excited about Jai, I can't wait. Yeah, I can't wait either. Super excited. I feel like that's gonna be... it's gonna be cool to try. I'm not saying I probably won't like switch over to Jai 100% or anything, but it will be interesting to try. I feel like it's sort of like a C style language with good features that you want. Like, I'm sort of feeling right now when I'm doing this project that there are definitely features that I wish I had, which just aren't in C, right? So it makes me have to write sort of ugly code just because I have to, which, you know, I think it's fine. Like, again, a programming language is never gonna make you a better coder, or it's never a good programming language is never gonna make better code, in my opinion at least. But it will be interesting to try, and if it's really good and if I really like it, I might switch over to making my project in Jai. We'll see how like the debugging support and stuff is. But I'm definitely excited to try it. I've been following that for quite some time now, and I saw that it's sending out. Beta keys as well, so that's cool. So probably it's on the horizon. That would be super nice. What do you guys think about John's like coding style, like his more data-oriented style of writing? Like, I was very resistant to it at first, but it's sort of like something that it has worn me down, I guess, lately, or over the past like years. Just since that's the way I used to code before. Like, when I started coding, it was very much like, you know, solve the problems I have, work in a very data-oriented way, because I was in an engine that was very data-oriented. But then I sort of went into more like, you know, like, oh, inheritance, that was pretty neat. And then it's like, oh, I'll virtual everything. And actors and such. I feel like it's just lately been like, fuck, this is so complicated. It's so hard to do anything because it just becomes so complex so fast. I think it's sometimes reinventing the wheel, like ranting on object-oriented programming, but basically implementing inheritance, use different syntax. Yeah, I do agree that I don't very much like people who poo-poo on object-oriented programming too hard, like him and you know, Casey. What is his last name? Minatori, I think, his friend, and also, you know, Mike Acton. And I feel like some people some programmers have gotten into the mindset that, you know, this way is better, and I'm willing to give them the credit that, you know, data-oriented programming has very good positives. But I feel like, again, it's the same thing where just because it has positive doesn't mean it will make automatically better code. And it doesn't solve every problem in the best way. I don't know. Casey's worse, yeah, I guess. I haven't actually seen that much of Casey. I thought I did watch this, like, was it like 10 million, 200 million line problem or whatever it's called. It's pretty interesting, but I don't follow him that much. I did buy the Handmade Hero thing and look at the source code a little bit. It was weird. This was quite interesting. But yeah, I feel like I have a hard time with Mike Acton. I feel like he's super good, like obviously top tier programmer, like one of probably the best. But his personality is, I guess, a bit more harsh than I like. Yeah, The Witness is crazy good. It's probably one of my favorite games ever. It's insane. Like just the technology behind it, but also just the game design. How hard it is to make a game like that. Like making a puzzle game in itself is very hard, but then making a puzzle game that is math focused and keeping it fresh and keeping it good and making it sort of easy to understand, but also like finding that perfect balance of easy to understand but still have the complexity to force you to think and be creative. It's so incredibly hard to do. I tried to do something like that at school once, when I went to Future Games here in Sweden. We had a school project and we did something similar. We said, oh, we'll do a sort of puzzle game that is very like pattern seeking focused and stuff like that. And it was very humbling how hard it was to make it good. Like how much it was like we made a puzzle and was like, this isn't fun. It's either too hard and too complicated, or when you get it, it's just boring. It's like, oh, I got it now, and then everything else just becomes boring. Like having it be that's perfect balance is so incredibly difficult. I'm stuck on a puzzle that's in the bottom of the mountain. Yeah, I haven't actually gone there far. I've gotten to the top of the mountain with the guys like standing there. They have to go like between the legs and stuff, but I still got stuck there. I should finish it though, at some point. At some point. Alright. So, we want to reflect the projectile, so when I hit something, I want it to sort of bounce off in some direction. Do you use the defer like macro in C++? Yes, I actually do. I use it in most cases where it's, yeah, I mean, I guess I use it where I would use some sort of stack struct otherwise. Like here, I think. Okay, most resource loading I use defer. Maybe I don't anymore. Maybe I switched away from it. I don't think I did. Maybe it's not here, maybe it's in like material. Yeah, here it is. So here, for example, I'm loading a file, and then I want to be like, oh, just remember to free it at the end of this function. Then I like to do defer, because then it's in the same place. But I don't know, I've been sort of I'm a little bit like, you know, I could just write free here. I guess the nice thing when you don't know the exit, path, then it's nice to have defer. But that usually doesn't happen. So then I don't know. It's like here it would be nice. So here it's like I'm loading a dat document and then I want to free it, right? So it could exit through any of these exit points, right? But I don't know which one, so then I want to make sure that it's deferred and stuff like that. The one is brilliant too. We managed to fit like 3 or 4 puzzles in a single screen. Yeah, I'm always amazed about how creative you really managed to get with those things. Interesting. How did you implement this? Yeah, I just have the defer file here. This is exactly the way that Jan Blow implements it. I have a struct. this is like the only time I actually have lambdas and methods is when I do this defer. So I'm saying like, okay, I don't want to use constructors, destructors throughout this. I don't want to use that except for this. I'm thinking defer sort of replaces, which is what it's supposed to do in Jai as well. It sort of replaces destructors, right? It's a replacement for that. So yeah, it's kind of like you just do defer, and then you make this defer helper, right? So you make this defer helper object, and as a plus operator, it does. It just returns. Oh yeah, that's what it do. You make a defer helper, and then as a plus operator, you make this defer actual stack object, right? So the reason you want to do this is because then you get this plus thing. Then you don't need to do like defer and then in parentheses do the code, right, or anything like that. So you can just do defer and then, whoops, defer and then just write in brackets what you want to do. The only thing that's so like almost perfect is that you'd have to do a fucking semicolon at the end. So you have to do like, oh, do things, and then you have to do a semicolon at the end, which is, you know, a bit whack. As well as a CPP con, I think, they talk about declarative programming. I have not seen it, and I actually don't know what that means even. I'm not very read up on declarative programming. I should check that. I'm gonna write it down right now. Was that John Blow who had that talk? Whoops. Oh shit, everything's going to hell. That's cool. I'll check that out. Thanks for the tip. But yeah, I like the fur. Kind of. I mean, yeah. My I brought it up with my lead at work, and he had a very good point. That it sort of doesn't work the way sometimes it doesn't really work the way you would expect it to work. For example, doing something like, you know, char maybe allocate something. Like you don't know if it's gonna allocate or something for some reason, and then you would do like, oh, if pointer, then defer delete pointer. Right, something like that, where you would expect this to work, but of course defer, like this will be a block right in here, so it will use defer right away, so we'll delete the pointer in this if statement, right? So it sort of becomes a little bit weird when you think about it. Like you can't do an if defer. I guess you would have to do some sort of if defer and then have the if statement in here, if defer pointer, then delete pointer or something like that, which becomes a little bit ugly. I wouldn't say that's like a hard-hitting, like, you know, it's not like a super point to make, but I do think it's valid that it's like sometimes you expect it to work one way, but then it doesn't. So that's the only criticism that I really heard of it, and sometimes I think like I mean, makes everything a little bit more magic as well. There's like, oh, it's gonna happen sometime, you don't really know, like, you know, when you're writing it, like, free the thing and it happens right away, it's a little bit more easier to follow the flow of what's happening, you know. So I don't know.
CPP con?
Oh shit, I do have it, but I'm also like, you know, a little bit careful. It's Andre Alexander's declarative control flow. Sick. I will check this out. This seems super interesting. I feel like I wanna learn more about different types of programming as well. Very interesting. All right, so let's continue on with this. So, okay, I wanted to reflect. I want the bullet to be like and like reflect off the units, right? So I'm gonna do reflect. Since now we have the cool like normal data that we didn't have before, so now I can do like reflect direction on the unit hit normal. Right. Should I make the projectile? Because the problem is my game is like in 2 dimensions and 3 dimensions at the same time. My projectiles and units are actually like their positions are Vec2s. Their positions are Vec2s. I'm like so on the fence if I should just make them Vec3s. Like why not, right? Like why not make them Vec3s? Because like the game is top down, right? So it's like it's sort of like from a like theoretical standpoint is to the game, but then I might want like, you know, height differences as well, maybe. I'm deferring this. Get it? I'm deferring this till later. That decision will have to be future me. Excuse me? Oh, right. So this will be a vector. So now I have to do this, like, you know, swapping back and forth all the time between Vec2 and Vec3. So hopefully now, what's gonna happen is I'm gonna shoot this dude, and the bullet's gonna bounce off of him and go, like, up here somewhere. Bang. Okay, I missed him. Great. Bang. Okay, I missed him again. Fantastic. Bang. Oh! Okay, so there he went. He, like, went off for some reason. I'm wondering if he got actually hit, like, 1 billion times or something. That doesn't look good. Yeah, it's definitely getting hit more times. So that's not good. I wonder why that's happening. I mean, it might be because we're moving the bullets into... We might pull back a little bit. Maybe we should do a little bit of pullback. Yeah, maybe we should move it out a little bit. So, okay, so let's do that. So let's do it so that we move the projectile out of the way. With normal. By a little bit. So do a little bit of pullback of the hit. And see if that maybe does better. Bang, bang. Yeah, there we go. What? I got hit from behind. What? Oh. Oh, he's shooting at me. Okay, I got you. So it's, I'm getting like pulled into him. Oh yeah, that's because... Oh, okay, now I understand why it's happening. Right, so the thing is that... Okay, yeah, okay, so this makes sense. So the problem is that we're reflecting... Okay, so I don't think we can actually do this. We're reflecting the direction of the projectile, but I'm setting this pointer here, right? So say like, okay, this is a unit we're gonna hit. Don't do hitting yet. Like, just like save it for later. So what's happening is that when we're getting to actually hitting, we're saying, okay, get an impulse. This is the impulse you should get from the hit, right? But we're saying get an impulse in the projectile's direction, which made sense before because the bullet sort of like went like bang, and then it's like, oh, I'm done now. So then it's like sort of got pushed that way. But now it's actually bouncing off, right? So when it's bouncing off, then it's saying, okay, get an impulse in this direction. So it's sort of pulling the unit with it. So of course we want to do, might want to just do maybe save the hit in that case. So we'll do hit results, units, hit. Oh, that's not that's not pretty. We have hit unit and unit hit. You know what? It's fine. Hit results. What we'll do instead. I have to do some renaming here. What we'll do instead is that we'll give it we'll give the unit an impulse in the reverse of the normal, right? So if we're hitting, so much shit. If we have a little volleyball, and then like bang, okay, we hit here, bang bang, it's big pain. Okay, the projectile is going off in this way. It's being reflected upon this normal, right? Whoops. So what we're expecting, since it's sort of like, you know, forces like it's a reaction and it's an action and a reaction, right? The projectile is being bounced off, which means that the ball should suffer a force in the opposite direction, right? So since the projectile is getting a force in this direction, we expect the ball to get a force in the opposite direction. So it's actually going to get an impulse in the opposite of the normal. So then we'll say you will have an impulse in the unit hit result normal minus. Of course, that's Vec 2. Gosh darn it. Okay, so now let's see what happens. So bang. Okay, I missed a bang. There we go. That actually looks pretty cool. I don't know if that's actually what we want. No, now that I'm playing when it feels really weird. I think we want the units to actually get pushed back. I gotta fix the line renderer as well. The line drawer is just out of whack. I'm pretty sure we want the units to move forward anyways, because it just becomes super hard to aim at them if they're gonna like bounce around like that. It makes them feel like marbles more than like a unit that we're hitting. So I'm gonna quickly revert that. Say like hell no. And instead we will... What's the best way to do this? I guess we'll just save an impulse here. Yeah, let's do hit impulse. Impulse equals... and then we just do the save it as the projectile direction before we destroy it with the reflect. Like that. The projectile trail start should be changed after reflection, no? Yes, exactly. Right now it's on a timer, so I do like points, right? I do a point and then I move, and then I do another point and then I move from there. We should, when the line drawer, since it's moving, the line drawer is moving like I'm making a trail. When the line drawer changes direction very sharply, it should put a point there. So it should say like, okay, I've changed direction here, so put a point there. Like we should subdivide here and start going from there forward. So that's what we should do. It's also gonna look kind of whack actually. I need to remake the line drawer. Is really bad. it's really bad. So at some point I have to go in and fix that. What was I doing? Oh yeah, okay, so now we save the hit impulse here. So now we actually don't need to save the hit. Let's just do hit results. Let's just call it hit. Okay, and then here we'll do hit impulse. F vector? What is this? Unreal? Vector. Okay, there we go. So now the bullet's being bounced off, but the unit is still being pushed back the same amount. Obviously, it's not how. At least I'm not. I mean, maybe one gun will work like this. It's not how this gun is gonna work. But it was just to sort of show off a little bit what we sort of can do with the hit results that are kind of nice. Pretty neat. Pretty neat. I'm gonna take a quick toilet break and then we'll continue on. 1 second. All right. We crack on. I want to do one last thing before I think I'll end the stream. I want to do some sort of more general way to query the scene. So now we have the sort of testing specific shapes to each other. We can test lines with spheres and so on. But I want to have a way to sort of test the scene itself, to be like, okay, I have this ray or this line, run through the scene and try it against all the units and everything, whatever is there, and then give me the result of that. So that, for example, in the projectile, we don't need to do this manually every time, but instead the scene will sort of do it for us. And then we can at the same time query against props, so stuff like walls and the ground, if we want to do that, and so on. Fantastic. So let's do that. So we will do... I wonder if I can place this in a scene, or if I should do another... I might do... Whoops. I might just do a new file for this. I think it's gonna be better. I'm already kind of scaring my include tree, since more things are including game, and game is including a bunch of things. So we'll do scene query, we'll call it. So it will return a scene query result. That's gonna have a hit result in it, and it's also gonna have like a unit to be hit. I guess it's called unit. To say like, oh, you hit something, and also there was this unit, right? So you can say like, oh, did I hit like just a wall, or did I hit the unit? That's what we're gonna do. So we'll do, excuse me, we'll do engine collision head test, and we will declare a unit. So we'll do scene. Oh, whoops. Scene query results. Query scene. I guess we'll do line first. So we'll send it in a line to be like, okay, query this line, and then it should give us a result to see what we hit. Seems good to me. So this will just kind of do what the projectile is doing right now. So let's just copy this. So we'll do. Whoops. Oh god. Okay, there we go. We'll do this. So maybe we'll not do this. Oh yeah, we're gonna have to do exception settings later on. Oh well, we'll fix that up when it comes to it. So we'll go through all the scene units. We're gonna include scene. We get the unit sphere, and then we test line sphere, and then instead of doing this, we're gonna do results upon hits. And if it has a hit, then we set the result, unit is equal to unit, and return. So then we'll do query all units. Great. So then in projectile, instead of doing all of this, we will instead do hello Stenbeck, I'm a long time fan of you as well. I wanna watch your stream, dude. You should start streaming again. Stenbeck TV is gone but not forgotten. Scene query results. So we're querying the scene. This music is perfect. Oh yeah, you're waiting for fiber, that's right. Man, I can't wait. This playlist is just like waiting for you to come back, dude. Like every time I play this playlist on my stream, I always think about your stream. So let's see. Query results. So we're gonna query the scene with a line. So we'll do query. Whoops. This naming is not good. We'll do scene query line instead. So scene query line. Yeah, for sure. Dude, you, me, and Jacob fucking broing up, playing games or just hanging. Just fucking can't wait. So let's see, scene query line. Move line. Broing up. That's what you do. The query line. The move line. Like so. So maybe we'll actually do this a little bit up here instead. Alright, so then we query. So then we check if the query result has hit. Then we check. Okay, so we get the unit out of it. So unit equals query result unit. And if there is a unit, and if we have a unit and we have an owner and do I save owner? Oh yeah, I do. And we have an owner and we have control over the owner, then we hit the unit. So we hit the unit with that fractal owner, and then we can actually do this direction times 20. And then we'll go back to destroying the projectile. Bouncing was nice, but we'll keep it out for now. Then we wanna, yeah, then we're done. That's good, because that means we need to include stuff. So that's what we want to do. Let's call sync query. Stenbeck, I want you to see this. It's my game. The arrow thingy, that's just like a dot in, it's the same as a dot in AniScript. It's in C++ for some reason they was like, oh, let's do arrows. Arrows are cool. So that's it. That's exactly the same thing. Move line. So you know, like when you do like, oh, my actor dot position. That's the same thing. Where in C++ you would do like my actor arrow position. Here, move line. That's wrong. This is supposed to be line. Oh, of course, it's supposed to just return the results. Yeah, I mean, if you're in Visual Studio, it just sort of auto changes it. So if you type a dot, it makes it into an arrow. But in the program I'm using, it's not doing that. So it's just two key presses, and you have to do like shift arrow as well. So it sucks. It's a big baloney. Here's my game. Look, I can shoot these guys, bang bang, and they like retaliate, so they shoot at the one who shot them. So then they're just like, oh no, you shot me, so now they're gonna kill each other. And he's like idling, so I can be like bang bang bang, and now he's gonna chase me, and he's gonna shoot that guy. Whoops, and then no, he shot me, but bam, he's gonna kill him. Yeah, it's like 3D, dude, but it's like 2D at the same time. Look, and I can go to like BAM, like editor mode. Like check him out. It's ML engine, man. It's the dick engine. It's the power of my engine. Like I can have like a laser beam. I can collide with stuff. Yeah, the shadows are a bit fucked right now. I don't know, what are you seeing? I mean, The thing is that right now I'm not giving much sense of like perspective or what's happening. It's supposed to be like a top-down view, and we're like walking around in a top-down view, right? And I can spin around to spin the camera around, but oh, I mean like the yeah. I've been told that they sort of fuck with people, especially when you spin around. It sort of looks a bit weird. So yeah, this will change for sure to be like actual objects and stuff. There's a lot of the graphics that are needs a lot of work, for sure. Yeah, it's a little bit weird. Thanks, bro. I think I can get to something. I can make it look okay at the end. But yeah, there's for sure a lot of things I need to do. A lot of work. A lot of work that needs to be done. But at some point, I will push this actually. Oh shit! Sorry, Ropel. Actually, you asked me a long time ago if this game is open source, and it is right now. So you can go check it out if you want. It's see, I can post a link in the chat. I hope you're still here. Actually, I might have left. Here it is. So there's a source code if you want it. Do whatever it is you want to do. So yeah, I want to push this. So like so. Right. So now probably I want to add some sort of obstacle in the way. Like it can just be a sphere for now, but later on it's gonna be like, you know, meshes and stuff. So let's start with just adding a sphere. So we'll have like a scene, and we'll do like a, you know, sphere obstacle. We'll just call it that. So we'll set its origin to be a bit far away. So we set it at like 500. And we'll set its direction to be... No, direction, that's nothing. Radius. So we'll set it to be, I don't know, 2? Something like that. So then we'll make sure when we render... Let's see here, let's draw, render. We'll also make sure to render the things as well. I will just do an update actually. So that's our obstacle. So preferably we're gonna collide with that. like either by walking into it or by shooting into it. So it should just this should be a no pass zone. So yeah, so in the scene query, we're not only going to query all units, we're also going to query obstacle. So we're going to do results hit is equal to test line sphere line and scene obstacle, like so. There we go. So now I can't shoot. I cannot shoot through this sphere. I can walk through it right now, but we'll fix that in a second. But at least I can shoot through it, so that's pretty good. So I can use this as cover from the dudes, right? Sort of move around, shoot a little bit, and then they will shoot into the sphere, and I'm safe. Ah, fuck. So also we could use this to be like, okay, they do a line trace or a line check to see like, okay, is my vision blocked by something? And if it is, then I'm gonna have to like move up and, you know, try to find the player somehow and not keep shooting at him. So yes, okay, so we did that. And now let's do the players or the units collision. So the units can actually, so they can't walk into stuff. It's gonna be a bit weird because they have like sphere collisions and we're gonna do line collisions, but that's fine. We'll make it work. So we're gonna go into units, and I guess on move, so here move direction. Here, instead of you moving right out, flat out, we're gonna do some collision stuff. So let's think about this. Yeah, so we'll do move delta will be their norm times units, like so, and then we'll do a scene query results. And now we have the annoying thing that these are all vec 2s, so we have to do vec 3s. And I guess we'll do half a unit up. Yeah, this becomes a nightmare to write, but whatever. I'll deal with it some other day. And then I guess we can do this. The dumb way first to see if it works. So we'll do this like if query results hit has hit, then just return. What music is this? Well, this song is "I Could Have Danced All Night" by Melody Sweeting. This is just a playlist that Stenbeck TV has Stenbeck TV has made. It's very nice. It's relaxing. Just you know, just chilling music. You know, I think that fits perfectly. Right, that's the problem. So okay, so a problem we had before that was like, I'll solve it later. We don't need to solve it right now. We're gonna have to solve it right now. Which is that okay? I'm querying a line in the scene to see like, okay, can we actually move this way, or are we hitting something? Would you mind sharing the playlist? I love it. Of course, of course. Actually, I'll ask Stenbeck first. You know what? I'll ask Stenbeck if he's okay with me sharing it. I don't know. I don't want. Just want to make sure. I don't know if you can actually share like non-editable playlists. Let's go see. Just give me 1 sec. Let's see. Can you make share? I guess you can just make a play. Yeah, I guess you can share the link. You can't edit it on its own. I guess it should be fine. We'll see what it says though. All right. So the problem is that you can't walk because we're querying the scene. We're querying the scene, and we're immediately getting a hit because we're hitting the unit that's moving. Like, so I'm trying to move, I'm querying, but I'm hitting myself with my own line query. So we're gonna have to do some. We're gonna have to do a bit of stuff. So we're gonna have to do a little bit of like. We have to do some sort of query. I guess sync query params, I guess. So some parameters that we can send in, and one of them is gonna be ignore units. It's gonna be one param. So we're gonna say like, if we're hitting this unit, you just move on. We don't care. So do params. Params then equals sync query params. We'll make it an optional parameter. So then in unit we want to send in a param. So we'll do scene query params, and we'll set ignore unit to be this unit. Alright, I have permission, so here you go. Here's the amazing, absolutely amazing playlist for my good friend Stenbeck. It's ultra chill and relaxing music of many genres. Oh, I will tag it. Yeah, no worries, man. No worries. He was very happy to share it. Alright, so we have unresolved. Of course, we have to do this. And then now we can check if unit is equal to the params ignore units, then we continue. So now, move. Yes. Okay, so it works. So we can move. We're gonna have some issues though, because if I go into this sphere here, like we're gonna sort of get stuck. Like I can get out of it, like it's not really stuck for real, but I can't move to the sides. Like it's very sticky. Like it's like I'm sticking to walls, which is very annoying and very. It just doesn't feel great, honestly. So that's a problem, and I also can not move into. I actually can. Alright, that's because their hitbox is at like the top of their. Alright, so we can actually move into other units. Okay, so that's, you know, Oh well, whatever. I should make these capsules later on, or at least cylinders, but you know what's whatever. You should collision check one axis at a time to fix that. It will give you a slide against wall feeling. Yes, that is one way to do it. That is one very excellent way to do it. So you could definitely do that. You could check against one axis at a time. That is one way to do it. The problem with that, the problem with checking one axis at a time, is that we can actually try it. Let's just try it out, and we can sort of see it's happening. But there will be small issues that we'll find with taking that approach. But I haven't tried it in a long time, so let's just try it. I'm just like, for my own curiosity, I kind of want to see what happens. It might just work fine. I might just be making mountains out of molehills. So let's see here. So we have the move delta here. So we'll just split the So we'll just split out the delta into horizontal and vertical. So we'll do like move delta x is just the move delta x, move delta to x and 0, and then move delta y is this y, like so. So now we split it up into x and y, and then we'll do this twice. So we'll do this one for x and one for y. So we'll do this, and then we'll just do start, and then move delta x, do the stuff, and then if it succeeds we do, and then I guess we'll just sort of flip this like so, and then we'll do the same for move delta y. Like so. Okay, so let's see. Oh, of course I spawned in the sphere. Okay, so there we go. So now I'm out. Okay, so if I'm moving towards this now, if I go upwards on the sphere, you'll see I sort of get stuck. Anyways, I can get out of it by moving away from it, in the x-axis. Like so, okay, so I'm getting stuck in the y-axis, right? Because I'm moving upwards. Ignore that I'm sort of, ignore that I'm kind of inside of it. I'm doing a line trace from the middle of the character. That's why I'm getting inside of it. In reality, I should do like a capsule trace or something, but I don't have that yet. So at some point I will change that. But for now, you can see that I sort of get stuck in the y-axis. But it's true. It is true that I can get out now by hitting left, right? So I can hit left and sort of get out still in an easier way. Before I could not do that. Before, if I hit left, I would still get stuck because the top, the upwards and left would still be inside of the sphere. So I would still get stuck. However, like I can't move left, which like kind of makes sense, like but still, what I would want to happen is that if I hit up now, I sort of slide against this. Checking axis or axis is more appropriate for AAB conclusions. Yes, that is correct. That is exactly right. So this approach works perfectly with AABB collisions. Then it's probably the best way to do it, I would say. Like, it's very simple, it's very cheap, you don't have to do much, you split up the deltas and do 2 line traces, which is fine. So then it's a great approach, and I mean it works better in here as well, but it does work perfectly. So for more complex collisions, then unfortunately we're gonna have to do something a little bit different. We can do something similar, like it's sort of like doing this is sort of a shorthand way of doing the more complex thing that we're gonna do now, which is that if we sort of look at this in Paint. Yes, exactly, it's that we're dealing with a sphere, and also that we're dealing with hitting walls that are not axis aligned, right? So this will happen as well if we had this situation, right? If we had like a slanted cube. So a cube that's not axis aligned, right? So a bounding box is the bounding box. And we walked straight up into it like this. And it would be like bonk. And we wouldn't slide against this, like we would expect to slide this way, right? And then just keep going, right? So what we can do, and this is what you do in like, this is what we do what I would do like at work, where we're making like a 3D game where you walk around. If we will make like a 3D, just a 3D walking game in general, is that you let's see here. So we draw. Let's draw like a flat surface. Gets kind of nice. Dalek asks, "Hello, what OS are you using?" I'm using Windows. This is Windows. I just have the thing on the right. I think it's nice to have it on the right, because then you have like the free on the bottom. I think it's nice. But yeah, it's just Windows. I am gonna port this to Linux at some point though. This engine. At some point I want to port it to Linux. I don't know exactly when. At some point that's happening, because I do like I do like Linux as like a concept, but so okay, so what we want to do is that, okay, let's say we have this movement vector here, right? So we're moving and it's like bang, we're hitting this wall, bang, we hit against the wall. What we want to do, we're not gonna do this fully the whole way, we're gonna do a part of it. What we want to do is that we're gonna take, okay, we move this vector, and it got blocked. This vector did not work. So what we want to do is that we want to constrain the vector. We want to say like, okay, what normal did we hit? Okay, so we hit this normal here. So we say, okay, we're hitting that normal. Let's slide against that normal instead. So we say like, okay, let's constrain our vector to that normal. So we say like, okay, constrain it to that normal, which means that take away everything of the vector, take everything away from the vector that's aligned with the normal. So what we're left with is completely perpendicular to the normal. So we're gonna constrain it, which means like taking away everything that's aligned with the normal, and we will be left with this vector here. So this will be our new movement vector. And then we say, okay, move with that vector instead. So then say, we hit the wall with this, take away everything, like sort of take away the energy that got absorbed by hitting the wall, and then move with the remaining. Is it not like the dot vector of the direction you're moving and the normal? I might be wrong. Alright. Yes it is. You're completely right. It's you take away the dot product, that's what you're doing. So you're taking the dot of the normal of the wall and the direction you're going, you're taking a dot of that, and then you take away that much, right? So you are on a completely right track. Which means that, okay, so let's say we're hitting a wall straight on, right? So we're like bonking straight into here, aye. So then we say, okay, the normal is pointing straight down, right? And since the dot product in this case, like our movement vector and the normal, it's gonna be 1, right? If we think of them as normal vectors, like it's gonna be the whole vector. So what's gonna happen is that you're just gonna cut off the whole vector and be left with nothing, because like, you know, since they are aligning, they're parallel, the dot product is gonna be 1 in this case. And that's what we expect, right? If we're running straight into a wall, we expect it to be nothing. We expect to just ram our head into the wall and don't slide at all. That's what we're expecting. But if we have just a little bit, like it's a little bit of slanting, right? So let's say we have, I'll draw the same box again. Let's draw something that's like super kinda almost not even slanting, right? This. And we're like bonking into it, right? Bang. The normal is like this. Now they're almost perpendicular. Like the two vectors are almost perpendicular, almost at a 90-degree angle, which means the dot product is going to be very small. Which means we're going to take away a small amount of the vector. So we're going to take away like this little part, like this is what we're going to take away, this little vector here. And we're going to be left with this. Which means that we're going to move quite quickly against the wall. We're going to slide much faster against this wall than we will slide against like this wall, right? That's almost a 45-degree angle. So that's what we're expecting. The more like sort of we just like sort of touching the wall, the more we get sort of like redirect a little bit and keep moving. But the more it's sort of a solid wall, the more we're sort of slowly inching our way to the edge and then keep going. All right. So let's do that. So let's just do. So we'll go back to what we had before. See, like so, and then we'll do like so. So then what we want to do is that we want to constrain the move delta. So we want to say like, okay, you hit something, it was a wall, too bad. Then we constrain it. Then we say like, okay, move delta is equal to constrain to plane. Move delta, we're going to constrain that to the wall plane. So that's going to be query result hit normal. And constraining to the plane just means that if we have a plane, right? So here's like a plane, a flat plane, and it has some vector and some normal vector here, right? If we have another vector pointing away from it, or like under it, let's say this one is pointing downwards, constraining it, like here's the shadow of the vector, right? Let's say here's the shadow of the other vector. Constraining it means just bringing it down to the plane. So it won't preserve the length, it will only preserve sort of the directionality from the perspective of the plane. It will bring it straight down to the plane. That's why we say it's constraining to it. So we'll constrain it downwards like this. And this one will also be constrained downwards like this. So we sort of lie flat on the plane instead. And that's what we want in this case, right? Because right now the plane is facing horizontally, right? This. Like here's the plane pointing outwards. And our movement vector is sort of pointing away from it like this, into the wall, right? It's sort of hard to see, but imagine this is going into the wall. Maybe if I do like this, maybe it will make more sense. So here's the arrow. So constraining it in this case means like, okay, bring it to the closest point on the plane. So that would be like somewhere over here, right? So here's this shadow. Then we're going to bring it down here. And by constraining it, it will be perpendicular to the plane. Or I guess, sorry, I guess it's like parallel with the plane like itself, but it's perpendicular to the plane normal. Anyways, that's what we're gonna do. So let's see here, what we were doing. We're doing query results, blah blah blah. Okay, so we're constraining to plane, move delta hits normal. Of course, the move delta is a vector 2, so we're just gonna take the vector 2 of normal, and we have to make sure to normalize it as well. So we don't care about how the wall is pointing up and down, we're treating it as if it's a flat wall anyways. So if we're running up against a sphere, like the bottom of a sphere, we don't want to go downwards, we want to just like treat it as if it is a flat wall and just constrain that way. And that should give us the same results. Right, so that's right. So now if I go upwards here, I'm expected to slide against the sphere. So let's see what happens. And there we go. I slid against it. So I got... And then I slide sideways until I'm free, and then I keep going forward. And I can hit right to slide the other way. Mathematics, bro! Amazing! Mathematics is the way of life. What a beaut. Amazing. So now we have this. Yes. What was I gonna say? Right? Math and classical music, dude. It was like, it's a match made in heaven. I feel like it's like, even when you're feeling down, you're like, this algorithms, man, it's too hard. I'm feeling down, feeling confidence low. You sort of relax, you listen to the music. What is this? Stranger in Paradise? Never heard in my life. But it calms me down, and it gives me confidence. And that's all that matters. Right. So I want to do one last thing before we sort of wrap it up. By the way, thank you all for joining, all the viewers out there. Thank you for writing, interacting. It's what I want this stream to be. I want this to sort of be more of a educational style thing, where I work on my project and everything, but I wanted to use the game I'm making as sort of a catalyst for teaching just random stuff about whatever, mathematics, programming, whatever people want to know. So I'm always very happy to see that people are joining in. So what I want to do for the last part of the stream is I want to do it so when I move past this sort of sphere here, so you see this guy is pissed off, he's trying to shoot me, he's trying to kill me. When I move past this point, I want him to sort of realize that, oh no, I don't have vision of him, like something's blocking my way, and he's gonna, I guess for now we'll just make him forget about it. We'll just say like, he de-aggroes, I guess would be the thing we will do. So we'll say like, he's behind wall, de-aggro, don't do anything. Hey, and I'm glad you found your way here as well there, though. So sorry. You're always welcome. So okay, so that's gonna be the last thing. It's gonna be cool. It's gonna be great. Later on, of course, we're gonna do something like maybe they pathfind or something to be like, oh shit, he's behind cover. We'll do some maneuvering or something. I think it's not the most fun mechanic ever that they sort of forget about you. It sounds a bit very gamey and not very fun. But for now, we'll baby steps. That's game development. Take baby steps. So the thing that's controlling these enemies is called a mob, right? So a mob in my game is the brain of a computer-controlled AI, or in this case, I guess it is like an enemy player. I guess if we had like friendlies or something, I would maybe not call them mobs. But that's at least the terminology I've gone for. That mobs means the brain of a unit that's controlled by the server to sort of hunt down and kill the player in some way. So it's not the unit itself. The mob is not the unit itself. The mob is a brain controlling the unit. So that being said, the mob of course is the one that has the aggro timer, it has like the shoot timer, it has everything that controls how the AI should work, basically. So it has this here aggro target. So I guess we can just check all the time. We check. I guess later on we're gonna do something like check every 5 seconds or something. But right now let's just do on update on tick. We just check like, okay, is the vision to the aggro target clear? And if it isn't, then we reset the aggro target. We say like, okay, I'm not aggro anymore. So yes, okay. So let's see here. So we have a server update. Here it's doing some timer stuff, idle timer. Okay, so here's the shoot target unit. So here's an if statement saying like, okay, if we have a target unit, then like, aim towards it and do some shooting stuff. Shooty woody. So then we'll also do a query. So we'll do a scene query. Query results. To be scene query line. I guess we'll do a vision line. So we'll do like vision line. And the vision line is gonna start. Whoops. It's gonna start at the unit itself, so that's gonna be unit position. Whoops. I will change the unit position to be vector 3. I'm so this is getting out of hand how often I have to type this. So it will start at the unit's position, like the mob's controlled unit, and it will end at the target unit. So we'll shoot target unit position, and then we'll query that line. So we'll do vision line. Yep. And if the query results comes up with some hit, so we say if the hit has hit, it's kind of weird to type honestly, and this is important, and we don't hit a unit, right? So we hit some sort of geometry or something around, like yeah, I guess it's now it's just like the sphere we have. But we don't care if a unit is standing in the way. We don't care about that. We only care if it's something else is standing in the way. If that's the case, whoops, then we will, if that is the case, then we will set mob, set aggro to null pointer. And I guess we return, I suppose. Because I kind of don't want this to run. There's no like break if statement, which I wish there were. But that's fine. Oh yeah, we have to include stuff. That's great. Okay, so let's see. So I'll aggro this guy, bang. Okay, so he's aggroed and he's shooting at me, so that's great. And now I'm gonna walk past this sphere, and hopefully... Okay, so that's not great, and I think I know why actually. It's because it's the same reason. It's the same reason why the collision of the player was bugged before, and it's because the query is hitting himself. Like the query is hitting the unit itself, since that's where the line is starting. So we're gonna have to do the same thing. Unfortunately, we're gonna have to do the same thing. We will do a params, and we'll set ignore unit to be the units. Set that as the params, and then will be bang. He's angry. And then I move behind here and dang it, he's still angry. Okay, so I wonder what he's hitting. I guess we will just sort of this is something I kind of wanted to do anyways. Maybe yeah, I will do this. So let's do this. Let's do okay, so let's do this. Let's do in the query params, we're gonna have draw, or render, debug render. And we're gonna have a, debug render duration. So we're gonna have an option, if we want to, we can debug draw what's happening in the query. Like this is a very common a very common thing to have in engines, like in, you know, I don't actually know if they have it in Unity, they probably do, but at least in Unreal it's almost hard to turn off debug rendering for the queries. So we will do, see what's the best way to do this. I guess we'll do it here. I guess we'll make a function. Just do scene draw hit results. Whoops. Hit position, and then we'll make it red. And we will also draw the normal. So we'll do hit position, hit normal, oh, hit position, oops, plus normal. And make it red and do filtration. So then here we can do maybe it's best to do this actually. Let's do this. So let's do line draw. So let's see. So if hit has hit. Okay, so if we have a hit, we want to draw the line from the start of the line. From the start of the line to the hit position in red, and then we want to draw the point, like the position, the impact point, and we want to and we want to draw the normal. Okay, but if we didn't hit anything, we just want to draw the line in green, which means like, oh, you did the square, but you didn't hit anything. Like so. So then we'll hit the unit, and then we'll do scene, draw, line, query, results. line. Maybe I can do this actually. Maybe I can defer this. I've never used deferred in this way, but I guess we can. I guess we can do it. What did I call it? Debug render. I don't know if it's a bit dirty to use defer like this, but you know what? I don't care. Sometimes you just have to do dirty things. Oh, whoops. Result. Scene draw line. What? Alright, yeah, we can only do this if we're clients. Okay, so let's see. So I will. Oh, right, I never used it. Should do it first. So we go into mob, and then in the params we will do debug draw. Debug render is true. So let's see. So I will hit a bang, and we're not getting anything because it's only happening in the server. Right. That's why. So let's do this on the client as well, but just only act on it if you're the server, I guess. So come here, and he's gonna query, and it's not gonna hit this thing. All right, of course, of course. So if it hits a okay, yeah, okay, so this is something I'm gonna have to... Yeah, with this we have to fix. So it's... So its problem is that we're checking all the units first. We're checking all the units first, right, in the same query. Here. So we're querying all the units, and if we hit the unit, we just get out. We don't care if something else came before it, right? Because it's like, here we're testing the sphere, but the sphere is ahead of the unit, like it's in front of the unit, so it should be hit first. The problem is that as soon as we detect that we're hitting the unit, we're early outing anyways, no matter if something is in front of it or not. So that's the problem. Okay, so we'll do this instead. We'll do... then we don't need to defer this actually. Yeah, okay. This probably is a better way to write it in general. So then we have result, I'll move that down. So we'll do a query result for all of the passes. So we'll do unit results. For how long have you been making games? Jag ska ta online 4H efter OG-post man hinner snoka. Welcome Anton. Yeah, I've been streaming for a long time today. My throat is getting quite fucked. But it's fine. We're almost done. Just one last thing. And I've been making games since I was 9 years old. So I'm 26 now. So that means 17 years. Is that from Django? Oh, is that music from Django? Is that what you mean? Maybe this music is like random, chill, nice music. It's very nice. Django Reinhardt. Sounded like minor swing. Oh yeah, it is a minor swing. It's from Chocolate, apparently. Or wait, I don't actually know. Chocolate, sorry. Some sort of movie. Did you see when you were 9 as well? No, I did not. I started out with Game Maker actually. Like a 2D game engine. It was very nice. I love Game Maker. I think it's quite brilliantly set up. Honestly, it's very data oriented. But then I moved on to C++ when I was like, I don't know, 14, maybe 15. I don't remember. Then I went to Java for a while. Then I went to C# for a while. Now I'm back in C++. So I've been around the block. Have we tried GM2? No? Is that the new version? Do you mean like the first GM2, or do you mean like is that some new thing? Game Maker Studio 2. I haven't even heard of this. I feel like I should get back to Game Maker at some point. Just like be like, you know what, I'm done with this. Back to Game Maker I go. You should try it though. It's a good engine. Good engino. What am I doing? Right, okay, so we're gonna have to choose a hit result somehow. I mean, know the fluff, you can skip it and make games. Yeah, it's true. I would miss C++ though, for sure. What are you using to render, OpenGL or DirectX? I'm using OpenGL to render. OpenGL is my jam, but that DirectX is fine as well. I've never used DirectX ever, so maybe it isn't fine. Maybe it is the worst. I have no idea, but it's probably good. This is like quickly becoming the standard of the industry. Like HLSL, I feel like HLSL is like the almost becoming like the language to write in now. So like even if you're making platform independent code, usually it's like something like HLSL anyways. What's the best way to do this? God, my brain is completely fried. I'll just make the simplest possible way. It'll have to do. So we'll do results, and then we'll do hit results, hit, and then we'll do then if hit has hit and and hit time is less than results hit time, then we'll replace the results. So we'll do replace hit is equal to hit, and also we set the result hit time to be big number for now. Then we'll do hit result hit is equal to this, and if the same thing here, if hit has hit and hit time is less than result hit time, then we'll replace it. Then we'll say result hit is equal to hit and result unit is equal to null pointer. There we go. So this should work. What do you mean big numbers unidentified? How dare you? Oh, I made small number but not big number. What should big number be, you guys? Let's check what Unreal does. What's big number in Unreal? What? There's no answers. Oh, whoops. Actually, don't I have Unreal installed? I might have Unreal installed actually, so let's just check it out. Check this one out. So we'll open folder. Whoops. Train game, arena script, select folder, and then we'll just do a search for big number. Yeah, because sometimes you don't want a small number, you want like, it's kind of small. You know? See if it finds anything. I should probably have done a better search path. Whatever. We're getting there. Let's do a little dance. Come on. You can do it. Okay, well I'll make it easier. Where? I want to search in engine source. Maybe I can find it myself. Math. Oh, okay, no wait. Oh, okay. Wait, no. Oh It's not math here. It's like engine maybe. No, core probably. It's like who will find it first, me or Sublime Text? There it is. Okay, so big number is defined as 3e, 3.4 to the power of 38, or to times 10 to the power of 38. So that's kind of random. I'm guessing that's an important number in some case for floating point stuff. So you know what? I'll take their word for it, and I will use that. Whoops. So just copy that. I will also actually wrap these in. That is a good idea to wrap these in brackets to avoid tomfoolery. Oh, whoops. Have you been using Unreal as well? Yes, a lot. I work at work. We use Unreal, so I've used that engine quite a lot. But I used on Unity as well. I like those engines. Okay, so now see if we're good citizens, then yes. Okay, there we go. The trace is ending up on the sphere, and it's getting a collision there, and the server crashed. So that's fantastic. So okay, so the server crashed. So why did that happen? I'm guessing it's in here. I would be hella surprised if it's not in here. Yeah, okay, so this is why. So it's setting unit ID, and of course unit is a null pointer, so we're dereferencing a null pointer. Ew. Can't do that. So we have to make sure when we set aggro that we want this to be able to be an index smaller than 0. So we say like if ID is bigger than 0, then do this. Oh wait, never mind. So if it's smaller than 0, then we used to aggro. Oops. Aggro target is unit handle. Yes. Otherwise, get the units from the scene. Like so. And then when we set the aggro, when we send it over, so send it over the network channel, we can check if the unit, if units, then send it units ID, or else send, and then we don't want to write U32, we want to write I32, then we want to write -1. So if we're sending a -1 in the network message, that means we don't have a target. It should be null pointer. So here we go. Okay, bang. Okay, so he's aggroed to us now, and he's like ray tracing all the time. I can also dodge his bullets quite easily. This is concerning. Should probably work on that. Okay, and now, okay, so there, I went to the cover, and he immediately let go of the aggro. So if I aggro this guy and then go into cover, then it's fine. And if I aggro this guy and go into cover, then it's fine as well. So great. Fantastic, it works. And I can be like, oh, go into cover, and then, go into cover. Oh, yeah, okay, so that's a bug. So one bug is that if I aggro a guy and go into cover, but I might maybe if I make them stop moving. If I do like, let's comment this out, I guess. So here's a bug. I know how to fix it. I won't fix it today, but I'll fix it next time maybe. So if... Just waiting for them to spawn a bit. Okay, I'll spawn one here somewhere would be good. This looks strange. Okay, that's not a good spawn. He's in the dome of pain. Okay, they're spawning in exactly the wrong way. I want to spawn here. Come on. Oh my god. Okay, so... Okay, at least make the spawning go faster. Wait. I want to show this before we end the stream. So here, excuse me, we will do spawn interval to be like 2. It's just gonna spawn really quickly. Oh! Let's already have a server open. There we go, so now it's gonna be like bang bang bang, spawn a bunch of people. Oh yeah, the variance is still 5, so it can still take longer. Okay, this works. Okay, so look at this. I will aggro this guy, bang. And then I will go into cover here, but the scene query is still hitting this unit. So that's the bug. I am behind cover, but the scene query is not hitting the sphere. It's hitting a unit, and I've hard coded that if the collision here, if the collision is hitting a unit, we don't care. We say like, okay, I don't want to be blocked, like I don't care if my vision is blocked by another unit, I still want to shoot. So we have hard-coded that. The problem then is that if we hit the unit, then it will say like, oh, I hit a unit, so I should keep aggro, even though we're actually are behind cover as well, behind the unit it hit. So what we're gonna have to do is that we're gonna have to do in this query params, we're gonna have to have some sort of flag that says like, which objects do you actually want to query for? So we will be able to say like, I want to query the scene, but don't query units at all. Like, just ignore units. I only want to see, is there something else in between me and this target? So that's what we're gonna have to do later as a common, like a query mask, I guess is what you sometimes call it or something. We'll do that next time or something, when we'll see when I get around to it. But yeah, otherwise this was a very, very productive stream. I got a lot done. We got some cool stuff going, so now we have like, you know, actual walls and stuff that you can walk into. Like, that's quite an achievement compared to like before, we had actually nothing. And now we have actually something. And we have like hiding the hub cover and stuff. It's pretty cool. I'm pretty happy with this session. Don't know what that is. Ah, whatever. It's probably fine. Opportunity unit 0. Should I just spawn a unit or something? I don't know. Oh well. Thanks everyone for joining. Thanks for dropping by. I will probably stream maybe tomorrow or the day after tomorrow or so. Next week I'm gonna be have the week off, so I'm probably gonna stream a whole bunch. So hopefully I see you guys very soon. So thanks guys. See ya.